All right. Welcome, everybody, to Standing for Truth. My name is Donny Budinsky, and I am your host and moderator for tonight's Great Age of the Earth Showdown. It is a privilege to have two experienced debaters, two true professionals here with me to engage the question: is radiometric dating compatible with a young Earth? And I'm excited for a good, solid technical debate on an important topic, the age of the Earth and radiometric dating. Gentlemen, if we could, let's get acquainted, kind of break the ice a little bit before we get into the debate itself and our first opening statement. Catz, why don't we start with you? It's been a little while since I've hosted you in a debate, and so I hope you've been well. And Catz, can you tell us a little bit about yourself?
Yeah, well, I hope you've been well too as well. I always enjoy it over here. Like, I think you run a good, good shows, really nice and friendly back and forth. And obviously, I've spoke with TRock before, and got a lot of respect for the guy. So I'm looking forward to this. I'm a science teacher for 20 years. So I'm not full time teaching science now, but I still work in education. And just on the side, I've got a YouTube channel called Culture Catz. Changed it from Conspiracy Catz now, Culture Catz, that just looks at weird scientific stories and things going on that I think people might find interesting. And that's it, really. Other than that, I'm pretty boring.
Well, I appreciate it, Catz. You always make for a good exchange and a good debate. And so I would say you're entertaining rather than boring. And okay, if people want to see more from you, then I'll make sure that the YouTube channel of yours is linked. Looks like we do have at least a couple of your channels here linked in the live chat for people.
Wow.
There you go, for people to check out. So, okay, Catz, appreciate that intro. Great to have you, of course. TRock, great to have you as well. You're certainly no stranger to debates, nor is Cat. So that's why I think this will be an Age of the Earth debate to remember. And so, TRock, how have you been? And a little bit about yourself.
I've been good. I've been extremely busy. I do a lot of different things. I'm kind of all over the place. Al, thanks for joining us. Me and Al spoke sometime. It's been a while. What's it been? 3 years or more? It was pre-COVID, wasn't it?
Yeah, long time now.
So we had a discussion. It was more of a discussion than a debate. Al was very hospitable. I appreciated that. It was specifically on Isochron Dating. I don't know if Al's gone back and reviewed any of that information in preparation for this particular discussion, but anyway, thanks to the audience for tuning in. You guys really make it worth it, especially at Q&A time. So my official position is that the Earth is about 6,000 years old, plus or minus 200 years. That we know that specifically from the Bible. As far as the scientific evidence goes, it's perfectly consistent with that across a broad number of sciences, all of them pretty much. But I'm looking forward to this discussion. So thank you, guys.
Thank you, TRock. I appreciate the introduction. Thanks for the introductions from the both of you gentlemen. I know that you both dig deep and you are well equipped to discuss these topics. So again, I'm excited to see what you're both going to bring to the table for tonight. Again, for anybody just joining us, the debate question for tonight is radiometric dating compatible with a young Earth? TRock is taking the affirmative, Catz taking the negative. Now, tonight's format is going to go like this. We're going to have 15-minute opening statements, followed by 10-minute rebuttals, uninterrupted rebuttals. Then we're going to jump into a free-flowing discussion of about 40 minutes. Then we'll have a 5-minute closing statement where our guests tonight can wrap up their thoughts and points. And then this is where we get you guys in the audience involved. We'll have a roughly 25 to 30-minute audience Q&A. And so please, if you do have a question, let me know who the question's for, TRock or Catz, and do your best to tag me either at Standing for Truth or at Donny. And let's try and keep it on topic. Tonight's topic, the age of the Earth. TRock, we are now going to hand it over to you. I'll get the timer ready. 15 minutes. And I do see your screen shared at the bottom. There we go. And you just let me know when you're ready, TRock.
He's going to get a quick preview of all my slides. I started in the wrong position for whatever reason.
There's a sneak preview.
Okay, I'm good to go.
Okay.
Radiometric dating, is it reliable? I'll be honest with you. I just read the debate question posted on the deal for the first time yesterday, so I'm fine with that. I do want to make the caveat. So I'm taking the affirmative position that radiometric dating is compatible with a young Earth, specifically because it's not technically a dating method at all, even though that's the way it's obviously perceived and presented. But the radiometric data is definitely consistent with a young Earth and with the biblical timeline of, like I said, 6,000 years, plus or minus a couple hundred. Okay, so a couple questions to ask. Does a reliable radiometric method imply that there is a pattern? And then ask the converse. Does a pattern in radiometric dating imply that it makes a reliable dating method? Well, the answer to the first question is a reliable radiometric method absolutely implies that there is a pattern. There has to be. But the converse is not true. If there's a pattern in radiometric data, does that imply that it makes a reliable dating method? Not at all. You can have all kinds of patterns, even patterns that superficially look like dating, like reliable dating patterns. But that doesn't mean that by default, because you see a pattern, it's a reliable dating method. It's just a basic deduction of good logic. What are the available radiometric methods? These are, of course, are not all of them. I just splashed on several of the more common, more well-known and more frequently used methods. Rubidium, strontium, uranium, lead, potassium, argon, uranium, thorium, carbon 14, argon. There's a quite a number of them. I wasn't attempting to list them all here, but we'll come back around. This is what an idealized isochron plot looks like. It's not meant to be actual data from anything. It's just kind of what it looks like. It may be a little bit misleading here. It may be accurate, but you can see that the y-axis is really small compared to the x-axis, and there's a reason for that. By necessity, these the y position has to be very, and actually the entire data cluster has to fit into a very, very small space in terms of numerics. Are there conflicting radiometric results? What is a valid isochron? What is a discordant date? What is a false isochron? What is a mixing line? And just kind of a random question about argon. Does 100% argon diffuse out of rocks before closure? Well, we'll answer all the questions, but I'll give the very quick response to each one of these. What is a valid isochron? Well, valid isochron basically means that it's not discordant and that the scientist or the literature in general agrees with the results. What is a discordant date? That means that the scientist or the literature does not agree with the date result. What is a false isochron? Well, it's essentially what looks like a valid isochron, but it's called that because it's a discordant date, because it literally does plot correctly like an isochron is expected to. What is a mixing line? A mixing line is, as I understand it, it's basically where it's another term for a false isochron. In other words, if you see the term mixing line in a results database, what they're saying is it's a discordant date. It's just another way of saying it. What they're saying is that the isotopic ratios seem to have homogenized in some way that make them appear like an isochron, when in reality, the scientist does not agree with the age assignment that it alludes to. Does 100% argon diffuse out of rocks before closure? No, absolutely not. The open literature acknowledges that, as well as some results that creation scientists have done in some of their studies, which lends itself to the immediate suspicion that radiometric dating isn't technically dating at all. Okay. So a couple of questions to ask and follow up here. How do you know whether a date is valid or discordant? Well, you got to have some other context to compare it to. And it's typically a geological context of some sort or a paleontological context to compare the results to know whether you're supposed to call it valid or discordant. What are you comparing it to? Well, like I said, it's typically you've got to compare it to the geological context. For example, if you have an igneous intrusion that goes through a Miocene layer, and you get a radiometric dating result that's older than the Miocene, you are going to immediately be suspect because the Miocene should have happened first and the intrusion should have happened second. So you have to compare it to something. If the rock cools on the argon issue, if the rock cools from the outside inward, how do you avoid having argon diffuse from the bottom toward the top without it being trapped by the cooling, by the rapid cooling of the outer layer? So just points to ponder about why you would use argon dating. Here I'm giving densities of several, some of the elements, some of the minerals that are involved here. Basalt 2.8 to 3.0 grams per centimeter cube. Granite slightly less, 2.65, 2.75. Zircon's quite a bit heavier than basalt or granite by a factor of about 1.4 or so over basalt, 1.5 over basalt. Uranium, very heavy compared to basalts and granites and zircon. Lead, much less dense than uranium, but much more so than the first three. Rubidium and strontium, however, are very light. Strontium looks almost on par with granite. But rubidium looks light enough that you would expect it to just flat out float in, very hot, low viscosity magmas. Half-life in years, just a quick reference, uranium-235, 700 million, uranium-238, 4.5 billion, lead-206, 4.5 billion. Interestingly, those two are very close to the assigned age of the Earth in terms of their half-life. Lead-207, 7 million, rubidium-87, 49 billion, potassium-40 for beta decay is 1.28 billion. And carbon-14 is 5,730. That's also very interesting because here we have the creationist version of a half-life that matches our, that very closely, it comes very close to our assigned age for the Earth. So I find that very interesting myself. More physical characteristics that are important to understand. Zircon, melting point, over 2,500 degrees Celsius. Basalt melting point is between 980 and 1260, and the granite melting point is 1215 to 1260. So upon very little reflection, you can kind of see a problem developing here. Zircons have such a high melting point that they can be melted, that the rock in which they reside can be melted. The zircons can be moved around and remelted later, and it doesn't destroy them at those lower melting temperatures for basalt and granite. They actually survive that. So that is very akin to the idea of contamination in carbon-14 dating. So with the density numbers in mind here, this is just kind of a rough idea of how this should play out in a normal physical world that we live in. So the red background is, roughly representing some type of hot magma or lava as it's coming out of the ground, whatever. And then the gray is lead and the green is uranium. And so you got a roughly homogeneous distribution of those throughout the magmas. Over time, though, because lead and uranium both are extremely dense compared to basalts, if the magma stays hot for very long, the first thing that should happen is it should start settling down to the bottom fairly quickly, especially with lower viscosity magmas. Donnie, quick check. Am I doing okay?
Yes, you're coming in good, TRock.
Thank you. Until finally, is a pattern emerging? Yes, the pattern's going to emerge out of this. if you have, and this is roughly distributed in the bottom, but if you have excessively more uranium than lead because of its density difference, it's going to get to the bottom quicker. And so you're going to get a pattern out of that. Now, bear in mind that this example, I am not talking about zircons at the moment. I'm talking about free isotopes outside of zircons. Although a very similar thing should happen with zircons, as we've seen from the density of zircon crystals themselves. They're quite a bit heavier than the basalts and granites in which they reside. Okay, so how big is a zircon crystal and how big is a single atom? It's not a great graphical representation. The atom, the little tiny dot in the middle, the red dot, would actually be much smaller than that compared to this size crystal. But keep that in mind because that concept's going to be important here in a minute. High temperature, low viscosity, longer time means more physical separation of the heavier elements in the liquid magmas. So how long does the evolutionist think any particular magmatic pool has been sitting there in its liquid state? I don't know, but you can't afford very much time because even 1 year is way too much given the density differences. Zircon colors, okay, because most radiometric dating, especially for the Earth, is determined by zircons and the Isochron method. I've kind of put a focus here, but there are a number of colors of zircons: yellow, green, red, reddish brown, blue. Those I think are probably just some of them, maybe more, but that's important. Does the color variation indicate a variety of chemical compositions? I believe actually it does, and it should, just like diamonds also have a variety of colors associated with them. And I believe it's due to the chemistry of the diamond and impurities and stuff like that get trapped inside of them during formation. Examples of distant dates: C14 coal, C14 in diamonds, erroneous dates in rocks of known age. I didn't put it specifically on here, but Mount St. Helens has been a center of focus for creation organizations that have done some of their own testing, and it's well known that rocks of known age do not yield correct ages. The typical response given by a critic or a skeptic is that they knew it wasn't going to, they picked the wrong method on purpose, and so on and so forth. And it is exactly that response that demonstrates why it is that radiometric dating is not reliable, and is not actually a dating method. It's because if you were to develop a standard, if you were to develop a control group for your testing, when you first set foot out the door to investigate radiometric dating, the first thing you would do is to develop a control group. And your control group would 100% be formations like Mount St. Helens that you know have happened inside of recorded history, where you know the age up front so you can compare your results to. This article here, I do recommend this article. It's very good. It's old, but it's very good. The information is still valid and pertinent. I would definitely check that out at creation.com. And finally, I'll close with this, recognizing the problem. This is one of many quotes that are out there in the literature. I'll go ahead and read it. Mr. Webster Smith regarded the atomic dating method, except in respect to carbon, as still very tentative, especially where the older rocks were concerned and where discordant and even absurd results were quite common. There were records of granites which automatically were older than other granites that they intruded. Argon was all too prone to be either deficient, wholly absent, or even too high. In such cases, the author adjusted his figures. And this is a quote I pulled from creation.com as a secondary reference, but the original reference is this at the bottom, Geological Society of London. So with that, I am going to relinquish my time. Thank you, Donny.
All right. Yeah. Thank you, TRock, for that roughly 15-minute opening statement. Catz, whenever you're ready, we're now going to hand it over to you. I'll restart the timer. You also have 15 minutes for an opening statement if you need to screen share. and show some slides or visual. There we go. I see it.
Okay, when does my time start?
You are good to go. Starting now, Kat.
Brilliant. Right. I've really been looking forward to this debate because a lot of the debates I do in the past, I've been trying to convince somebody of something. And it's very easy to just sit there and go, no, that's not good evidence. That's not good evidence. But if we see on screen, this is the title of the debate, okay? Does radiometric dating support the young Earth? And TRock's position is yes, it does. And my position is no, it doesn't. So by the very definition of the title of this debate, during this debate, TRock will need to present to me evidence that radiometric dating actually does say the Earth is 6,000 years old. The problem is there are literally no studies anywhere that actually say the Earth is 6,000 years old. So it's going to be very, very difficult for me to lose this debate, given the fact that the pressure is all on TRock to prove that it does, rather than, and I'm sure he won't do this during the debate, rather than just say radiometric dating is unreliable, because that's not the question in this debate. This debate is, does it support the young Earth? So we'll see when we wrap up at the end, does it support the young Earth? Or is the best we can do when we're answering this question to try and call into question the credibility of radiometric dating? Because if the best you can do when you are presented with the question, does it support the young Earth? If the best you can do is try and call into question its credibility, that means you openly admit that it doesn't support your stance. You're just scrambling desperately, if you like, to try and make it not support my stance. I'm sure that won't happen, but that's I just wanted to start the debate with that, because I am going to keep going back to that slide just to remind of the question. Now, I did debate TRock, and he is right, a couple of years ago, and was it a debate? It was a discussion. It was dead friendly. He was a really, really nice guy. I've got a lot of time for him. And we were talking about isochron dating. I've took this nice little screenshot of one of the things he said in that debate, and I want to look at this. I've created on PowerPoint, right, my own little pointer like that. How does that? That's well, I think it's pretty cool. He said here a few times that homogeneous, right, isochrons can be created by any mixture if it is homogeneous, right? Any mixture whatsoever if it's homogeneous. And I'm not really sure what he meant by that at the time, but the problem that TRock had with that at the time, and we, this was a nice friendly discussion, we didn't get too heavy into it, is that we aren't talking about homogeneous substances when we look at isochron dating. By the very definition of the explanation I'm about to give you, they cannot be homogeneous. And I've already seen a couple of questions in the chat of people saying, no, if it's homogeneous, that's why you get a straight line. And I'm really not sure. I didn't come away from the last debate really knowing what that argument was. Hopefully, TRock can elaborate on that today. But it really doesn't make any sense. Let me tell you why. So this is an isochron graph, as TRock correctly showed. And let me just explain a little bit. Well, I'm going to spend the rest of the time really explaining to everybody how isochron dating works, what the principle behind it is. Now, the principle behind isochron dating is that we can use it to prove that a system has been closed. In other words, we've had no contamination. We've had no leaking out of a substance. We've had no leaking in of a substance. And then that way, if we can prove that, then obviously the results are reliable. And when we use isochron dating, we find that the Earth is, millions and millions of years old, not 6,000 years old. So we are going to be able to rule out that kind of argument that, oh no, it's a little bit flawed because it may have been contaminated. So how do we do that? Well, if we look on the left here, let me just pop look at that. Technical genius. If we just pop this on the y-axis, strontium-87 and strontium-86 are stable isotopes of strontium, right? They're stable. So the ratio of strontium-87 to strontium-86, when we find strontium in minerals, isn't going to change because they are stable. So if I plot the minerals of a rock on a y-axis, and I'm looking across my y-axis here, these minerals here are all going to have that exact same ratio because they are stable isotopes, which is why they form a straight line when viewed from the y-axis. But that doesn't mean they're homogeneous, because these minerals are different minerals, not the same mineral, they are different minerals. They will all contain a different amount of rubidium-87. Now, rubidium-87 decays into strontium-86, which gives a real problem for, well, not for me, but for the young Earth point of view. And why does that give a problem? Well, when rubidium decays into strontium-86, the amount of rubidium decreases. So the ratio of rubidium to, rubidium-87, let me just get this right here. I'm not sure I said this. Rubidium-87 decays into strontium-87. I don't know if I misspoke there. So rubidium-87 decays into strontium-87. And that's the problem, because when rubidium decays, this ratio here goes down, right? The strontium-86 is stable, so this ratio goes down. So as this decay happens, all of these points are going to move over to the left because that ratio goes down. However, on the y-axis, this ratio is going to go up because we are gaining strontium-87, which means they're all going to go up. So in other words, they're all going to go up, and they're going to go up to the left. In the perfect scenario, if it is a closed system, as they move up to the left, they will all stay in a perfect line, and we have proved it's a closed system. Now, back to this homogeneous comment. This is simply not homogeneous. If we look at all the minerals we're using, they all have different amounts of rubidium. By the very definition of what I've just said there, it cannot be homogeneous because these minerals are different. They have different amounts of rubidium and a different rubidium to strontium-86 ratio. They are completely different. I'll also point out that it is the ratio that counts, not the total amount. So even the starting amount of these isotopes doesn't make any difference. So anyway, let's take this. This is one of the minerals on that graph. And we start off with our rubidium-87 and our strontium-86. And as time goes on and it decays, let's just have a look. As it decays, we can see that suddenly we start getting that increase in strontium-87, so that ratio is increasing, but we get our decreasing rubidium-87, so that ratio decreases. All right, but if nothing moves in and nothing moves out, we can see that this is a very, very predictable relationship. Yeah, as the amount of rubidium-87 halves, the amount of strontium-87 doubles, very, very, very predictable. And that is why we get, if I can just page down. Yeah, that is why in a system that is completely closed, we get this here, right? Based on the fact that it is not homogeneous. It's not homogeneous to start with. It's absolutely different to start with. But the way they decay, if they all decay in isolation without any contamination or anything leaking out, then they're all going to decay in a predictable way, and they all move upwards and to the left to produce a straight line, which is in line with the starting ratios that they had to begin with. However, if there is contamination, so let's say we have this as another mineral here. Here we can see when the rubidium decays, oh, look what happens there. Some strontium-86 washes into the sample, right? Maybe a little bit more as the decay goes on. Maybe things are leaking out. Right? In that situation, that is not a closed system. We're going to end up with something like this. We're going to end up with something that is so far from being a straight line that it's untrue. And a scientist will look at this and they will go, I can't use that. That's rubbish. I cannot use that to date this rock or whatever I'm dating because these things they simply don't form a straight line. All right. So we would throw that out. We wouldn't even try and use it. So this is why isochron dating is so powerful, because we know it's been a closed system when we get this. And as TRock actually said himself in a presentation he did with you just last week, TRock is happy that there's been no accelerated decay, you know, and he's happy that if there is no contamination, that we can use these ratios for dating. I remember it was like the practice presentation. I sneakily watched it. And he definitely said those things. So I know that TRock isn't going to come at me with like accelerated decay or anything like that. So this does pose a real problem to him. And it's absolutely not a homogeneous system. Let me just hit that one more time in case anyone else tells me this is homogeneous, right? This red one here is not the same as the green one or the blue one because all three of them have different amounts of rubidium compared to the different amounts of strontium. That is not homogeneous. That is not the same mixture. These are completely different minerals, not homogeneous. How long have I got left, Donny?
Good question. You have just over 5 minutes.
Okie dokie. Right. So, it's just over 5 minutes. So, I mean, that's really what I'd like, because what I wanted to make as the main thrust of my discussion. But like I said, I am going to bring it back to this question as often as I can. The title of the debate is radiometric dating reliable? All right. Let's stick to what the title of the debate is. Does radiometric dating support a young Earth? And if the answer to that is no, because all we're going to do is provide evidence that says, oh, I don't think radiometric dating is credible, then the answer is no. And I challenge TRock to admit that he cannot provide evidence that radiometric dating does support a young Earth. All he can do is try and find a way to discredit radiometric dating. Now, my experience, I don't do a lot of stuff with creationism. You know, I had a couple of fun debates with Ray Comfort and Kent Hovind. Me and you, Donny, have gone back and forth a couple of times. I really enjoyed those. But so I'm not really educated on the whole young Earth creationism. I might trip up on some things tonight that I should know about and I don't know about. You know, it's a good time to catch me, TRock, because it's not really my topic. But what I do see is this kind of pattern. I see that, you know, we have scientific evidence supported by literally all reputable scientists and literature. But when I look at debates involving creationists, the answer seems to be no, they're wrong, because the Bible is a historical, accurate document. Now, if we're going to use that argument, fine, use that argument and say, look, the Bible's historically accurate, but I haven't got any scientific evidence to back it up. And I'll be happy with that. I'll be happy to shake hand at the end of it and say, okay, you know, you think the Bible is historically accurate, that's where you're getting information from, but you admit that there's no science to back it up. And again, if there is science, you will provide that science in accordance with the question, which is this. You won't just try and discredit radiometric dating, because that isn't what you're trying to do. You're trying to say, yes, it is good. Other times I see people say, no, the science is wrong because, and they'll insert a really poor straw man here before then reverting to the Bible. And when I say poor straw men, I know there's some really famous examples. So when Dr. Austin did the St. Helens rock, which I've already seen pop up in the chat, where somebody laughed and said, oh, look, you know, that St. Helens rock was dated at nearly about 3 million years old. And we know when St. Helens erupted, etc. You know, these are straw man arguments. We know that the laboratory that he sent the specimen to had a margin of error in the dating that was carried out of 3 million years. So the best they could ever do, even before he set foot through the door, was to say somewhere in the last 3 million years, right? That's the best they could ever do. But yet these strawman arguments of, well, look at that, it only erupted a few years ago and they said it was 3 million years old, you know, are very dishonest if you know what you're doing. And we've got other, you know, strawmen dishonest arguments as well, haven't we? Like there is carbon-14 in diamonds. And here's a cracking little paper I bought, and that I found online, sorry, to show how diamonds, old diamonds, are actually used to measure the background radiation of the equipment that measures carbon-14, because essentially they are so deplete that they have, you know, virtually nothing detectable in them. And it's the background. This paper is great. And I've linked everything, actually. You can see all the links at the bottom of my slides because I will be bringing them and I'm happy to show them on screen. But what this technique does when you are testing these diamonds at a deplete of carbon-14 is you're actually testing the background radiation. You're using them to calibrate your equipment is what you're doing. And because, you know, of that background radiation, we're getting something of around about 50 to 70,000 years old. And that helps calibrate so we can kind of knock those readings. It's like, you know, detecting background radiation so you can knock it off your reading when you're trying to find how active a source is. So, you know, it's a bit dishonest to say, ooh, you know what, we found carbon-14 in diamonds. So I hope those aren't arguments that are going to appear tonight. And I do hope that I do see evidence to say, yes, look, this experiment definitely says radiometric dating supports a young Earth, rather than let's just discredit radiometric dating, because that's not the question. Let's debate the question. And I'm done.
Conspiracy Catz, thank you very much for that roughly 15-minute opening statement. Gentlemen, I appreciate the time, energy, and work you both put into those. Lots of points on the table for us to engage in rebuttals. And so we have 10 minutes on the clock for an uninterrupted rebuttal. TRock, we are going to hand it back to you whenever you're ready. Please go ahead. The floor is yours.
Donny, did I have my share screen button?
I don't see the slides.
Sorry,
You might have to
sorry.
screen
I
share.
gotcha.
As you're doing that, I'll remind the audience that we are doing an audience Q&A once we're through with our closing statements. And so please, if you do have a question for tonight's debaters on the age of the Earth, make sure to send those in. TRock, slides are up on the screen. You're good to go.
Okay, Al used this argument about homogeneity versus actual isochron plots. With all due respect, Al, I think you're basically just arguing semantics. I pointed this out during my presentation that by necessity, these plots, these points, they're basically a condensation of the number of the ratios that you get, and they by necessity have to fall into a very small area. The word homogeneous does not mean there are equal amounts of rubidium and equal amounts of strontium of each isotope. That's not what the word homogeneous means. It means that that whatever the ratio is, it has to be consistent, or it's not an isochron plot. Whatever the ratio is, it's uniform throughout the samples. What a lot of people don't know is that a typical isochron plot only includes around 6 or 8, maybe zircon samples, and so the ratios are measured in each one of the samples, and so that's all you get in your plot is 6 or 8. You might get as many as 10, 12, 15, 20 if somebody's done a lot of work on it. I actually went and pulled a video on zircon prep for radiometric dating, and it is quite a tedious process unless somebody's come up with a more automated way to do it. It's a very slow, tedious, manual thing to do. So you historically, especially historically where most of our data exists, you do not get a lot of plots. But the bottom line is the homogeneity argument is it's more semantics, and it looks like a misdirect or a misunderstanding of what the word means, because it simply means that if, for example, I've got 10 rubidiums and 1 strontium 87, that basically each zircon should be roughly that ratio. So I don't want to spend a whole lot of time on that, because I don't think he understood what I was actually saying with that. I'm gonna stop sharing my screen and just continue with my rebuttal. Okay, he says he wants to challenge me. He said something in the very beginning. He said, if I say the Earth is 6,000 years old via radiometric dating, I'm not saying that at all. That's never been my position. I caveated my position at the beginning because of this. Or supports a young Earth was another one of the phrases that he said. That is much more accurate. Radiometric data, as I caveated in the beginning, supports a young Earth. Can't refute old Earth is what he said. He said my position cannot be that I simply refute an old Earth. So if you paid attention to what I was doing in the slide with the whole density argument, the reality is that all of those heavy elements have not settled out to the bottom. And so by inspection in a physical system like that, the fact that they're not settled out the way they should be over deep time, that pretty much endorses that the event of liquefaction, expulsion, and solidification have all happened in a very short period of time, which makes them highly consistent with the young Earth. So I'll skip this part. He said they're very, very, very predictable. I'm going to say no. I've actually got some downloaded data that we can talk about from a government website, and very predictable. Again, he's got to go back to the question I asked at the beginning. Does a pattern imply that it's going to be a valid for dating? No. Is valid for dating imply that there should be a pattern? Yes. So we expect in young Earth creation thinking that there should be a pattern. At least I do. And then he talked about background radiation in C14. That's an interesting comment. I've not gotten to review the paper that he showed. I'd be interested in seeing that. One of my previous debate opponents shared one, and I went through and read it very thoroughly multiple times. And it seems to me that there is not a consensus among the critics of where this anomalous C14 reading is coming from, because Al seems to take the position that you're measuring background radiation, where others take the position that it's contamination. So he also said it's dishonest to say we found C14 in diamonds. I'm going to say absolutely not true. The particular paper that I read, and unfortunately I don't have it with me. I had a computer crash and some other things that have happened. I've lost a lot of my files, but I would really like to get that back, and the one that Al has referenced, so that we could compare them sometime. But in the paper that I read, they specifically at the very end of the paper, they specifically gave an opinion. It was given strictly as an opinion. It was not a quote unquote scientific conclusion at all. The scientists who spearheaded the experiment were basically asking the lab techs what they thought was happening, and the lab techs suspected microfractures in the diamond harboring a little bit of contamination. But they also speculated in the paper about something akin to what Al has called background radiation. They called it instrument noise. But the purpose of that particular paper, and this is really important in whether somebody's going to make a claim of dishonesty on behalf of the naysayers, this part's very important. The entire purpose of the paper that I read was to try to determine if diamonds could be used as a zero calibration standard for carbon-14 dating. They had tried a number of substances, and they were looking for something with absolute zero, and they could not find it. If they were looking for something with absolute zero, but they knew what Al thinks he knows, that it's background radiation, they would have plainly said, we can't have a zero reference. And if it's background radiation of any kind, instrument, any kind, it can easily be mathematically eliminated from the model and accounted for. It's actually a very poor logic to refer to background or instrument noise, because it would be apparent in every sample you did, no matter what the age was or what the expected age. Modern archaeological samples from 1500 years ago or whatever, you would have to mathematically remove them from those as well. Even if the impact is relatively minimal, you would still do it as a matter of good science. And I will end my rebuttal there.
Okay, thank you very much, TRock, for that roughly 10-minute rebuttal. To the audience, I am all caught up on questions. I appreciate how engaged everybody is. We got a solid mix of views in our live chat tonight. Okay, Catz, we are now going to hand it back to you. Whenever you're ready, you have up to 10 minutes for a rebuttal. Go ahead.
Can I just clarify? This obviously is the rebuttal. So am I addressing only what was said in the opening debate? Is that the idea? Not what's just been said there?
Opening, and then if there is some material in the rebuttal that pertains to things said in the opening, I'd be okay with that.
Okie dokie. So in terms of the debate question, which is the title of the show that we're all watching, does radiometric dating support young Earth? I was making a lot of notes during the beginning, and I was hoping for, like I said, some sort of argument that, listen, this study supported the young Earth, or this study supported the young Earth, or this study here supported the young Earth. But I haven't written any of those down because none were provided, which says to me that there are no studies out there that support the young Earth, because it will be weird for me to think that there are studies out there, but they've not been brought to the debate when the question is, does radiometric dating support the young Earth? So the fact that they haven't been brought, I mean, I'll go through what I've written and what I think of it, but and then I'll just touch a little bit more on the Isochron stuff. So at the beginning of your opening statement, you said, does a pattern equal reliable? We need to talk about that in the back and forth, because that isn't evidence that radiometric dating supports the young Earth. And it's not evidence that radiometric dating doesn't support an old Earth. It's a question. So we'll talk about that question in the back and forth. But at the minute, I don't think that really needs a rebuttal. I think it was more a question. You said the cluster has to fit into a small space, and you went on in your rebuttal then to talk about homogeneous. Let me just reiterate again. These are not homogeneous. When you said that the ratio is all about the ratios being the same, strontium-87 and strontium-86 are stable isotopes. So the ratio of strontium-87 to strontium-86 is going to be the same. Rubidium-87, well, at the start, it's going to be the same. Rubidium-87 is not stable. So when this decays, the ratio here is going to change on this x-axis, right? This ratio down here is absolutely going to change, because it's going to get smaller as the rubidium decreases. And as the rubidium decreases and becomes strontium-87, then over here, this one gets bigger. So I don't understand why you are saying that the ratios stay the same, and that I didn't understand what homogeneous meant. The ratios definitely change. They're definitely not homogeneous, because if they were homogeneous, the graph would look like this. That's what the graph would look like if they were homogeneous. But isochron plots don't look like that. They are spread out on a straight line. So they are not. I don't understand how anybody could think that they are homogeneous. So maybe we could get back into that. But that's wrong. Are there conflicting? You did ask the question. Are there conflicting results with radiometric dating? Now, I'll give two answers to that. One, if there are conflicting results and you're calling into question the validity of radiometric dating, then I'll bring you back here. You are not providing evidence that radiometric dating supports the young Earth. What you're doing is basically saying, no, it doesn't support the young Earth, because there's conflicting results in your eyes. So you are literally saying it doesn't support the young Earth. That's how I take it. You're also saying it doesn't support an old Earth. I appreciate that. But again, like I said, conflicting results, a very small minority of conflicting results, although we could also look at papers like this one, if I find it. Right, here we go. So, I mean, the Alandi asteroid, Alandi meteorite. And again, I put the link. I'm going to put the link to everything I bring tonight, so people can see that, it's a real thing, and you can, find it. So the Alandi asteroid was radiometrically dated using 3 different techniques. Here, I've circled one on the screen. The other one, if I just show. So we had an age here from, that's lead isochron regression. And then over here, we have, sorry, hang on, internal. Okay, so, and that fits exactly with another group called Bizarro, who studied the same asteroid, but this time using aluminium and magnesium. And it's indistinguishable from somebody else who did another completely different study, again, in a completely different year. So I can point to evidence that it does work, because I can find scientific studies where we are getting repeatedly the same answer. And I can go beyond that. I mean, I can show you this from a website I've linked at the top, where there are literally hundreds. This is the Abbey meteorite. We can see down here the source: 1967, 1970, 1979, 1982, 1973, 1983, 2010, so on. And this list actually went on and on and on for dozens and dozens and dozens of these. So I just took a short sample. All people testing the same meteorites coming up here, we can see, with virtually the same age. So I can show plenty of studies that show that it is reliable for an old Earth, but that's not the question. The question is it reliable for a young Earth? And you haven't shown any studies so far. Again, you said about argon, does it diffuse 100% out of something? That was a question, not a statement. I don't think that statement supports your stance. It was just a question. Does argon diffuse in and out of things? I'm not really sure if you were trying to make a point there, or just, I don't know what that was. You talked about zircon being heavy, yeah, okay. Again, I'm not sure how it goes anywhere to answering the question that's on here. And then he talked about the colors of zircon. So it sounds to me that you don't actually have, and I hope you're wrong, but it sounds to me that you don't actually have any evidence to support this question. You're not going to bring any studies or data or results that really would show that it supports a young Earth. You're going to try and discredit the fact that it doesn't support a young Earth, which is a different debate. And I think highlights the fact that there is just such a lack of evidence out there that it does support a young Earth. I think that's my rebuttal.
Okay, Catz, thank you very much for that roughly 10-minute rebuttal. Gentlemen, we're moving along nicely. That concludes our 15-minute opening statements and our 10-minute rebuttals. We're now entering everybody's favorite part of these debates, the open discussion. And so rather than a real strict cross-exam, we'll do our best to keep it free-flowing and organic. Catz, you just ended with your rebuttal, and therefore, TRock, why don't we allow you to pick the first topic or ask the first question? And we have roughly 40 minutes on the clock for discussion. If at any time you gentlemen want to share screen, just let me know and I'll put your slides up. TRock, go ahead. And just make sure to unmute.
Thank you. Okay. Just to be perfectly clear, Al, I really don't want to center the debate on this particular point. I just want to clear it up super fast on homogeneity. I don't think it's edifying to anybody to spend too much time on that. If you go back and watch the presentation I did during our first conversation a few years back, that isochron plot that I presented in that presentation kind of shows what I was getting at. I think you're misrepresenting or misunderstanding what homogeneity means in a sample like that. It's literally called a mixing line. If you want to homogenize something, you mix it. You thoroughly mix it so that you've got the same content throughout. If you're doing physics, you plan on bodies having a more or less homogeneous content in order to establish what the center of gravity of the body is. That does not imply that every single point is exactly, for example, 101 to 13 or some exact number, but it does imply, strongly implies, that it would be something very close to that, 101 to 14, 101 to 12, 101 to 13, hence why you get different positions on the graph. But the graph that I presented in our conversation specifically shows, if I'm remembering correctly, it shows that a logarithmic scale has to be used in order to get you to be able to see visually the distribution. If you don't use the logarithmic scale, you end up with them clustered so close together you can't tell where they lay visually, even though mathematically you can draw the line. So no, I'm not implying that they all have to fall in exactly the same place. I've actually said this in the past, that if they do, you have a dot, not a line. And I will tell you, it actually still does not, that in and of itself doesn't invalidate the isochron plot. What it says is every single crystal in the sample has the exact same ratio, hence the exact same date with zero variance, whereas isochron plots actually show a tiny bit of variance, but they're so close that you can still draw the line with them.
So can I just, I appreciate you don't want to spend the whole debate on this bit, but it is a big problem for, can I just show my screen for your stance? You see, I know you said you weren't talking about perfectly homogeneous, but this is the slide you showed me. Isochron plots can be generated from just about any mixture if it's homogeneous. Homogeneous states can simply be the result of physical mixing, and then you've shown a picture of something being mixed so it is homogeneous. Mm-hmm. You know, so it does sound as if you're saying that if you take a look at, you know, maybe not a microscopic look, but a little bit of a step back, you are going to see the same repeated pattern throughout that mixture. It sounds like what you're saying. But I would like to ask you something, because one thing I did say at the beginning is that often when there's some evidence provided, we get quite a poor explained straw man to say, no, that must be wrong. And I think the argument that you're making here is that when we do get an isochron plot, the scale is logarithmic. I mean, plenty of scales are logarithmic out there. Why does that mean that this is, well, two questions. Why does it mean it's wrong? And why, with a logarithmic scale, do they form a perfectly straight line? Because you could apply any scale you want, but if they're not going to fall in a straight line, they ain't going to fall in a straight line. So can you explain why that invalidates this?
My point was fairly clear at the beginning about the pattern. You can have all the patterns you want.
How? But can you explain that? Can you expand on that? Because I know you said that in the last debate, and I mean, I will take notes. Honestly, I will take, if you just one step at a time tell me what that means. I will take notes just so I can clarify and fully understand. But can you just like be really ultra specific in sentences of what you mean?
That term that I put up on my slide, mixing line, if you remember, there are actually about somewhere around 9 or 11 different terms that come from the standard literature that all mean essentially the exact same thing. False isochron is one, apparent isochron is another, mixing line is another one, but that word mixing line specifically tells you that your two daughter isotopes have been basically combined in such a way that they look like an isochron when they're really not.
Okay, and in what way? So like I'm quite happy just to specifically write down why it's wrong. And I know you listed off some types of isochron there. I'm not sure how that's specifically
fractionation.
Yeah, so if you can explain that to me, just so I know why it's wrong, then we can move on that. And as soon as you explain it to me, we can drop it. But I'm still completely none the wiser as to why the fact that, you know, we use a logarithmic scale on this graph somehow debunks the graph, debunks isochron dating. Just if you could just spell it out for me, and then I'll know.
I didn't say logarithmic scale debunks isochron dating. That's not what I said at all.
Okay, my apologies. But if you can tell me why it is debunked.
Like I said, that the whole argument is basically just semantics. I'm just pointing out that you have to have a logarithmic scale. In other words, you have to zoom in very close to see the distribution. And again, I said very plainly, you can discern it mathematically without doing that, but you can't see it visually. That's why it's done that way. But I never said that using a logarithmic scale invalidates isochron interpretations. Now, back to your original question, how does that mixing happen? That term mixing line came from the literature. I did not make it up. Creationists did not make it up. It's something that secular scientists use because what they're describing is called fractionation, where the isotopes drift from one, the ratios of them drift over time. It was assumed very early in the history of radiometric dating that heavy isotopes like rubidium or more like lead and uranium, it was assumed that they did not fractionate, but no studies were ever done. Well, now there are studies out there showing that that is quite possibly an issue that conflates whether you're really seeing an age out of isochron plots.
So when you say you drift, do you mean the isotopes are physically drifting out the sample, or are you talking about the drift on the graph as the ratios change?
I'll be honest with you, I'm not perfectly clear on that, but I think it's both.
Well, I'll be honest, I am a bit more clear on that, and it's not both. When we talk about this drift, we are talking about the movement on the graph, and the movement on the graph is due, of course, there is a ratio change, like I explained before, because what we're getting is a decrease in the rubidium as it decays into strontium-87.
Okay, can you stop for just a second right there? Can you stop for just a second right there?
Of course, can you?
I want to make this point crystal clear because it sounds like you did not really clarify this.
Okay.
When you do what you're doing right now, you're describing what happens from the time that the crystal forms to the time we measure it some alleged millions of years later. But the measurement, it's completely frozen in one position. And that's what you got. You have today's ratio. That's all you have. You do not see this drift from rubidium to strontium and from strontium to the other stable isotope. You don't see that. You only measure what you have today. So I want to clarify that, because it's not homogeneous when you say it changed from its initial state to today's measurement. It's, of course it's not, but it is, I'll use the word semi or approximately homogeneous, because if you have 8 different crystals that you're sampling, every one of them has to approximately equal, for example, 13 million years. They all have to approximately equal that. If any one of them does not approximately equal that, either your plot's bad or you have to throw it out.
Well, I mean, I did say at the beginning, if there has been contamination, things moving in and out, then the plot is bad, and they, we don't use it, and that's why this is such a good method.
But the plot is frozen today's measurements.
So how does that mean? Because if we go back to the title of the debate, it is, does radiometric dating support young Earth? Now, any single current ratio of isotopes we see in any sample, in anything in the world now, unless we're dealing with things with incredibly short half-lives, like you might find, in hospital, like medical isotopes and stuff, we are going to get a snapshot in time like that. So if you're saying that because we're seeing a snapshot, it's not reliable, then you're also saying that all of radiometric dating technique is not reliable for the same reason, which means you are not saying that radiometric dating supports a young Earth. You're saying it's all unreliable.
That's not what I'm saying. I did not say because we only see a snapshot, it's not reliable. I did not say that.
Okay, I'll let you clarify.
Actually, I've pointed this one very important position of mine out that you probably don't hear a lot of people say this, but if the Earth truly were 4.5 billion years old, you couldn't tell it anyway. There would be no way to know that for sure anyway, and the older the Earth is, the less likely you're going to be able to do that accurately. The younger the Earth is, the more accurately you would be able to do that.
Perfect, because 6,000 years is incredibly young. So therefore, you should have accurate radiometric dating techniques that have come back and said the Earth is 6,000 years old. But that's not the majority.
No, that is completely untrue.
But you've just said that it's easier the younger it is.
I said you could be more accurate the younger it is.
So 6,000 years is younger than billions of years or millions of years. So therefore, you must have studies that show it to be younger. Like your studies must be more accurate.
So to be perfectly clear, because I don't know that you are aware of me having ever said this, there is no physical chemical test you can do on Earth anywhere that can tell you the age of anything. None. There are 0.
So
I've said that multiple times in the past. You probably did not know I think that way, but that is true.
No, I understand that. In which case, if you are saying there's no test you can use to age something, are you saying that radiometric dating provides tests that age the Earth at being 6,000 years? Or are you saying it doesn't provide tests that age it at 6,000 years?
What I'm saying is 2 things. Obviously, I can't say that we can provide radiometric tests that show the Earth is 6,000. I can't say that because of my a priori that I already explained. The other thing is, does radiometric dating support young Earth? I caveated this. I would really appreciate it if you do this for me. I don't expect you to, but if you did, it'd be very nice.
Mm-hmm.
Does radiometric dating data support young Earth?
But that isn't the debate that I was offered or prepared for. That's a different debate.
Did you?
So
Let me ask you this
debate.
Let me ask you this. Did you honestly think that I believed that you can radiometric date something accurately?
Well, I was asked to debate you on the topic, does radiometric dating support the young Earth? And I know we were shared in an email thread where we all agreed on the title. So, yeah. I did think you thought that.
I personally have never thought you could radiometric date anything, even carbon-14 dating that is done for, like I alluded to earlier, mentioned archaeological context, even stuff like that. The only way you know you have the right answer, number one, is because you have an archaeological context to compare the answer to. And number two, the results have been calibrated. If they've been calibrated, that means they've been adjusted to match that. So even carbon-14 in a very young world where you supposedly do get a quote-unquote accurate age, it's only accurate because you've adjusted it to be accurate.
So was the historical or archaeological context with the meteorites from space? Because obviously they aren't culturally linked to,
That
we're not going to
is-
take a bit of pottery from I can see if you take a bit of pottery from a pyramid, you might date it at the same age of the pyramid or vice versa. And I get that you might use that to inform your answer. But when we've got literally dozens and dozens and dozens of people, teams over many, many years and decades, dating the same samples of meteorite and getting the same answers without any historical context, then that kind of blows that argument out the water, doesn't it?
No, it doesn't, because what I'm talking about is calibration here, calibration and calibration standards. And so archaeological context applies to carbon-14, geological context applies to studies on the specific age of the Earth, because even the ones where they go out and they get this rock from the moon and bring it back here and perform some radiometric isotope testing on it to try and get an age, it has a specific geological context to the people doing that study. And what they actually do is they take the results that they get from that and then they change it a little bit to account for the formation of the early solar system. So
have you got any evidence of that? Have you got any evidence of that? Have you got any evidence whatsoever that these ages, which if you look at the website, and we can look at it at the top, I can bring it up if you want. There is absolutely nothing in that website that says they do anything other than radiometrically date it. And they don't even always, we've got lead, we've got argon, we've got rubidium, strontium. We've got a variety of techniques. There is absolutely nothing in there whatsoever at all that says what they've actually then done is compare it to the beginning of the solar system and try and fudge the figures. That is absolutely not what's been done here.
Think about that logically for just a second. If you go get a rock from the moon and you bring it here and you perform radiometric dating and you get a result, are you literally saying that the rock on the moon is the exact same age as the Earth without adjusting the number at all?
Well, you get a result, and that is your result. And what I'm saying here is, but now whether you look at that and think, oh, there's contamination, I'll throw it out, or I'm going to stick with that result.
Simple, very simple, straightforward. Forget contamination. Just assume that you got an accurate result without any abnormal interference, and you got some number. Are you literally going to assign the age of the Earth to be exactly the same as the rock that you found on the moon?
What, to the day without any margin of error?
Did I say to the day? No.
Well, that's what I'm asking. Like, that's what I mean. Like, you.
No, margin of error. Take a margin of error, plus or minus 0.03%, whatever. Take a margin of error.
So if I'm taking a rock from the moon,
is the Earth the same age as the rock that you measured on the moon?
Oh, so right. Well, obviously the moon and the Earth are different ages. Yeah, of course.
Okay, but the assumption is not that the rock came from the moon. The assumption
these aren't moon rocks.
Huh?
These aren't moon. No, you're right.
No,
these aren't moon rocks.
You're referring to one that was found in Australia, right?
Well, there's about 12 of these meteorites, all with. This is only half of the table for Abbey, but there's 12 meteorites equally, as long as this, studied by many. We can bring it up and we can look at them all if you want, if you want to see how many there are. But there are literally dozens and dozens and dozens and dozens, all using different radiometric techniques, coming up with the same answer over decades. We've got 1967 to 2010 here, using different techniques, getting the same answer without consulting each other and without any archaeological context, because it's come from space. So there is no archaeological context.
Okay. There is absolutely an archaeological context. I don't know how you could say there isn't one, because if you just blindly go and pick a rock from somewhere and try and date it, you have no idea how old that rock really is, because it could have come from the Mount St. Helens eruption. You don't know. And I just pulled up, you can just go Google. And to answer your question, you asked this earlier, what evidence do I have that they took a rock and dated it and then added some time to it to account for the formation of the universe? I did this years ago. I went and looked up, just Googled how is the age of the Earth determined, and I went to I think at the time it was a U.S. government website. Right now it's National Geographic, but this particular one. But it says they have examined rocks from the moon and from meteorites, neither of which have been altered by the rock cycle. The same techniques of radiometric dating have been used on those rocks. All the data from Earth and beyond has led to the estimated age of 4.5 billion years. It's not measured directly. It never has been.
Well, I think if you look at these this website and we look at the papers that are linked from it, and we look at, I mean, there's so much more. What was the other website? The Allender, which again, we can look down here. Apologies if I'm pronouncing that wrong. Like I said, this isn't a topic area I'm used to really debating, so I might be pronouncing a lot of these things wrong. But the fact that there are so many of them, all giving it's taken over decades, all giving such a very similar age, right? Albeit with a tiny margin of error, okay? All giving a similar age. How can archaeological context account for this that just repeats over and over and over again? Can you explain to me how that archaeological context makes all these people decades apart?
I told you archaeological context doesn't do that for that type of dating.
So what is it? What is it that's wrong about these?
It's geological context.
Okay, what is that context?
Where did they get the rocks?
Well, we can find that out, but for example, you suggest a place and then tell me why it would be bad for these results. You suggest a place and tell me why that wouldn't work.
I'm suggesting that they tried to do what you would deem common sense. So if you really thought the Earth was old, it does make some sense to go to a place like the moon, pick up some meteoritic debris, date it, see, because the assumption is that debris has been floating around there in the asteroid belt or whatever and was part of the formation of the solar system at one time, and it would reflect more of a condition of the age of the Earth as a whole and or the solar system. Other common sense, so you talked about earthbound rocks, and that's perfectly fair. Common sense, if you thought the Earth was really ancient like that, you would go below basement level rock or very deep in the ocean crust, and that's where you would pick rocks and say, okay, these are from early formation. You wouldn't pull anything from a Cambrian age. You wouldn't pull anything from an Ordovician or even an Ediacaran. You wouldn't do that because you already think that they're well younger than the age of the Earth. So you go find a geological place where the rock does not seem to fit in any of the newer formations.
Okay, well, let's go back, though, to what you said, because I felt you said something that was important that we kind of moved away from. So I said, I said archaeological context, and yeah, I misquoted you there. Quite rightly, you told me. You said it was geological context. And you said, where did they get the rock, right? There's geological context. So what I'm saying is, could you give me an example of give me any geological context, give me any kind of thread of thought that all these scientists, decades apart, who use different radiometric techniques to date this, could end up having the same answer? What context could there possibly have been? Please just give me one example that would have led to this.
What physical circumstances could lead to that? Is that fair?
Well, you said geological context. So
there's a physical process that the Earth was formed by, right?
Well, yeah, so I'll just let you expand on it up until you get to the point where you tell me why this would lead them all to have the same age.
Ultimately, what you want to know is how did they all arrive at that, and how do you get so many different results that seem to point that way? That's kind of what you're really asking, right?
Yeah.
Okay. So and I didn't bring this data, I was going to do it. I lead an extremely busy life, and we've got limited time here anyway. But Mattman has done a tremendous job of pointing to some Proton 21 lab experiments and where they do Z-pinch experiments. Are you familiar with any of that?
I say I don't really look at this area much, so no, I don't know who
That's
Madman
fine.
is.
That's fine. You don't have to get distracted. I'm just going to give you the basic explanation. So in Z-pinch experiments in the Proton 21 labs, what happens is Z-pinch is the result, as I understand it, of like very finite arcing in Earth material, and what happens is you literally produce de novo heavy elements like what's used in radiometric dating, and it produces them in similar ratios to what you get in radiometric dating. And I think it makes a very valid point for how it is that you get the patterns that we get, because temperature, pressure, and electromagnetic forces have been at play in producing those elements. And they apparently, from the lab experiments that have been done, they tend to naturally be produced in those ratios.
Okay, I don't know how what you're saying can just be ultra clear, and just tell me the reason these scientists who did this all these radiometric dating techniques on all these different on the same sample over decades using different radioisotopes, they all come to the same answer, and the reason they did that was this particular geological context. If you can finish that for me, I'll be far clearer. Or even give an example. It doesn't have to be the right, it doesn't have to be the right one. Give me something that would make sense.
So I've already kind of pointed to this. If you're going to go out and get a sample and assume it's associated with the age of the Earth, you're going to have to go deep into the rock layer. So that's kind of critical.
Well, it's a meteorite. It landed on the ground. You didn't have to go. It landed on the ground. It was a meteorite. You just picked it up. You didn't have to dig for it.
Where did the rocks deep in the ground come from?
No. This here is a meteorite.
Okay, but
so it landed on the ground.
Where did the rocks deep in the ground come from? The ones that you would assign pre-Cambrian, pre-Ediacaran. Where did they come from? They literally, in the secular paradigm, they literally come from outer space in the form of meteors. And what I'm giving you is two different contexts. Now, you're saying meteors, and I've said that too. I'm not disagreeing with you. You're saying meteors, yes. Per the quote I read off of the internet article there from National Geographic, both meteors and rocks from Earth, both. And so pick which one you want. All I'm saying is,
I want this one.
All I'm saying is the one thing they do share in common is that they've undergone extreme heat and pressure.
Okay, so given that the rocks on Earth, don't age to exactly the same age as Abbey here, for example, or the other meteorites that are on this webpage, which I'm more than happy to bring up. Again, I understand that, given the fact that Earth is a planet in space, everything has been formed in space at some point. I totally understand that. We are floating around in space, so everything has been formed in space. But again, how can that make these people decades apart using radiometric dating with different radioisotopes? How can the fact that Earth was formed from stuff from space and so was this meteorite from space, how does that make people just say, okay, we'll just date it all the same? I don't like. What is the train of thought?
We're not going to date it all the same. That's not really what's supposed to be happening. What's supposed to be happening is they get the results they get and they are the same.
Exactly. And that's what's happened.
Are you familiar with what boundary conditions are?
Are you talking about statistical?
No, in physical systems.
Perhaps go on. Give us an example of what you mean.
I mean, it's very similar. The concepts are obviously, the words kind of tell you what it is, but the boundary conditions are what's happening on the outer edges of this process, or the inner edges, whatever. But there's typically transitions, like our atmosphere, for example. You don't just cold stop our atmosphere and then start deep space. There's a transition where the atmosphere gets lighter and lighter, right? Anyway, the point is, in boundary conditions where you get into those transition zones, boundary conditions can change the effects that you get. And so if you date a bunch of rocks using radiometric dates, that using those methods, and you get all these isotopic ratios that seem to be consistent, it tells me that they were all created under very similar circumstances. And I'm being completely agnostic in this statement to what the actual age of the Earth is. That's just what it implies. It implies that they were all formed or in very similar conditions.
But yeah, because this here is one meteorite. These aren't different meteorites that are being tested. This is, maybe I should have been a bit clearer. This is one meteorite that has been broken up and those samples tested by many, many people over many decades. So it has been formed in similar conditions because it's basically the same meteorite. But so my question is, either we accept the date, because you said you test it and the date you get is a date you get. Well, these are the dates they got for that same sample using different radiometric techniques, and they're all very, very much in line with each other. So, and they all say, you know, millions and millions of years, you're way longer than 6,000 years old. So how have they got to that independently of each other? Because of some kind of geological context. I don't understand.
Okay. So you'll have to pardon me, Al. I'm not trying to be facetious at all, but your screen's really small and I can't read a single letter hardly.
It is. I'm sorry. I'll see if I can blow it up for you. I was trying to fit as many examples on the screen as I could, and so, it was cutting a.
I think what you're describing is you've got a bunch of different methods. Is that what you're saying? No, you got rubidium, strontium.
Yeah, I'll try and show it. And I do apologize. I did try and get as many on the screen as I can. So down here, in fact, I've cut a load off the screen now, but we've got at least here 3. We've got an argon, isochron, we've got lead, we've got rubidium, strontium. So there's 3. Here are the dates, all very, very, very much in line with each other. We've got the error. And again, if we look at the people who did it, 1967, 1970, 79, 83. When you go down here, we get into the 2000s, 2010, for example, when you go lower. So it's the same asteroid, radiometrically dated using different isotopes, different techniques, getting the same answers decades apart from each other. And there are literally dozens and dozens and dozens and dozens and dozens of examples of this with different meteorites when you go on that website that's above. So how are they independently, if it's wrong, all getting to exactly the same wrong answer?
Okay, a couple points here. So your first 1, 2, 3, 4, 5 entries there are rubidium, strontium, and they were tested across a span of 25 years there. So what's going on? They're all rubidium, strontium. They're all the same meteorite. They're all supposed to have the same age. So that in and of itself does not make your argument. You have to combine that with the lead dating. Lead is what the next several you get to.
Which has the same age.
Lead. Okay,
yeah, it has the same age.
Now that brings me to my second point. You said independent of each other. That is unequivocally not true.
So is the argument that they somehow have cheated off each other, copied off each other?
No, listen. I please don't put words in my mouth. I did not say anything. I'm not accusing anybody of anything. What I'm saying is that in half-life calculations, independent measurements of half-life of many radioactive isotopes are not actually measured directly. They're measured indirectly by comparing their atomic characteristics to one that was measured directly. And I don't remember the hierarchy. I don't have this information in front of me, but it's something you can definitely research on your own time. But what happened is they basically determined as accurately as they could one particular isotope's half-life. And then from there, they just used nuclear physics to compare other isotopes to and essentially calibrate them against that. So they're not independent at all. That's point number 1.
Just run that by me again.
That's kind of important though, because
what you seem to be saying there is that, you know, they'll do the testing and then they'll just go, we've tested it. Let's look at this book and see what the answer should be. That sounds kind of like what you're trying to say there. When they've done this, if you can read the methods, you can go and you can find the Schema and Honda paper, right? The Goplan and Weatherall paper. You can find them and you can look at their mythology, and you can do that for the lead and the argon. You can find their papers and you can look at their mythology and you can see how, and they haven't, you know, done it like you said that at all. They've literally just radiometrically dated it, and then this is the answer they've been given, and they're all falling in line.
Okay, now to that point, I'm going to do something real quick. I would like to share my screen for a minute.
No problem.
And I will show you. I appreciate your trying not to put words in my mouth when you gave that little graphical explanation there. But there is a reality to how
TRock,
this.
and I just wanted to let you gentlemen know, excellent discussion so far. As you're sharing your screen, you guys have exactly 10 minutes left on the discussion.
Okay.
Well, I'll tell you what, TRock, because I think I've dominated with my PowerPoint now, so I promise you I will not bring anything up unless you ask for it, and just do all your stuff now.
Well, I've got this interesting. Oh, good. I can move that. Okay. Can you see my screen, Donnie?
Yes.
Okay. I went and did a lookup. So what I've got here, Al, tell me real quick. Have you ever done this? Have you ever downloaded an actual database of radiometric results?
Downloaded data. I mean, I've obviously, seen them on papers and websites and stuff such as this, but I've never gone to the trouble of putting them in a spreadsheet.
That's part of my point. Any one paper doesn't actually contain a database. At most, it refers to a database and gives the data from their particular study. That's what individual papers do. That's not a database, though. So
what I just showed you then, wouldn't that be a database? Because it's got lots and lots and lots of.
It's a subset of a database. It's not a database. A database is the compository in which you dump all of your data, not just a tiny subset like that. So this is from an actual database. I went and downloaded an official government database of radiometric results. Now I will say, not get the entire database. That's kind of important, but I did get a big chunk of it. I think I got roughly half of it, and I'm not sure why it didn't download the entire thing, but I've got about 6,000 results in here. Here, 440 in this particular page. What you're seeing is the explanations that they give in column B is where you get all these different explanations. The original data set is this page right here, and if I unfilter this, we'll see I've got 6,123 entries minus, not counting the header row there. But so it's the explanations that I was interested in. There are a number of a bunch. There's quite a few in this database where the scientists that produced the data did not agree with the results. And in a lot of cases they did, but it's a significant number in which they did not. And so what I did here, age interpreted from source, and I gave a condensed version of it here. But so we've got 439 different entries in the age interpretation from the source. And so if you just kind of cursory look through this, affected by hydrothermal, age constraint on sediment, age of basalt, age of crystallization, age of dacite dike. They've got all 439 variations on their interpretation of it. Zircon core age, youngest zircon component. What does that mean? Youngest protolith age. There are so many different deals in here on how they interpret their results. One of the points here that I want to make very clear especially to the audience, is that these databases, I manage a database at work. I'm a part of a small group of people that manages it. And I can tell you unequivocally that when you have a large number of people contributing to a database, the data tends to be very dirty. And this radiometric data is not different than that. It's very dirty. They do not even record all of their information the same way. And if we go through these sheets and start, I don't want to take too much of the time here on this, but look at that pseudo plateau. What's a pseudo plateau? Mixture modeled component, the median. These are calculation types here. Total gas, so on and so forth. This is how many apparent age counts, an apparent age is like an apparent isochron. It basically means that it looks like the age, but the scientist really doesn't think it's the correct age. The total isotopic count for that is 654, and 459 of them have an apparent age count. And when you go back and look at this data, you find that these scientists sometimes are not very consistent at how they enter. See how some of this stuff is a little bit scrambled? They're not even very consistent in how, look at this. Uranium, lead not captured. This is supposed to be the isotopic ratio defined like up here, but a whole bunch of them came out like this. And you can see they didn't even spell it the same way or say it exactly the same way. Not captured or not reported. These databases are a lot dirtier than what the critics like to claim. They're not nearly as clean as they say they are.
I mean, I'll be honest. What I think I've seen there is you've put a spreadsheet together, but I'm still none the wiser how that spreadsheet discredits the fact that over and over and over again we are getting radiometric dating results that concur with each other and put the Earth to be millions of years old, or rocks, or even stuff from the pyramids to be thousands of years old, or whatever. But I haven't ever seen anything that suggests any kind of radiometric dating result ever that even comes close to suggesting that the Earth is 6,000 years old, which obviously the title of today's debate is, does radiometric dating support the young Earth? And we haven't been able to see even a single study or result that shows it does support the young Earth, which says that those things don't exist. So it seems to me that all the young Earth creation side has left is to try and discredit radiometric dating. And I'm not sure that spreadsheet really does it. It just seems as if you've collected data with reasons that scientists might have looked at and gone, well, this is the reason for my uncertainty. Here's my margin of error, and this is the reason. Every scientific paper published has a limitation section. Every scientific paper, if it's a good one, it has a limitation section. And I'm sure you've pulled a lot of those things from the limitation sections. But that doesn't invalidate the paper. It just means that as scientists, they're aware of the limitations, and we try and reduce our margin of error by tightening those limitations up.
Okay, so a couple points. I mean, it's a fair question that you ask about how do you point to a young Earth is the way I would personally phrase it. How do you point to a young Earth with radiometric data? Well, part of it had to do with the physical characteristics of density and mixing and so forth. But it kind of takes me back to the Mount St. Helens and what I talked about earlier about where is the control group to establish how you would use radiometric dating? Where is that control group?
Is that to me for an answer, or
hopefully a short answer. But where's the control group that would have been developed back in the 30s or whenever for how you even approach radiometric dating as an actual geological construct?
Well, with isochron dating, because you are looking at the ratios of two stable isotopes we've gone through it, but because you're looking at the ratios, the starting amount of those isotopes is completely irrelevant. You don't need something to compare it to and say, well, this rock started with this amount or this rock started with this amount. We're looking at ratios of isotopes, and it simply doesn't matter. It's the ratios that count as long as we know the half-lives.
So you're saying the isochron plot is the control group?
I'm saying that what the isochron plot does, if it's done correctly, is it reduces the need, or it eliminates the need to know what the starting amount of parent isotope was, because it's the ratio that we're looking for. You don't need to know what the starting, obviously there's a difference between an absolute amount and a ratio. We all know that. And an isochron looks at the ratio, eliminating the need for an absolute amount.
Okay, I'm trying to get you to think critically and get the audience to think critically about what you just said. The isochron plot demonstrates that you have the consistent beginning and life history of the decay process.
No, you don't need the
But
life
it,
history. You need the ratio. That's
that
how it's.
ratio demonstrates that the life history is a constant decay rate. That's all I'm saying. I'm not saying it's different than any.
No, but you agree with constant decay rates. You said that on the
I
presentation
do.
on.
I do.
Yeah, yeah.
I unequivocally, and I don't have any qualms about that at all. I personally assume that if there were any variation in the decay, it would be too minor to basically say that, okay, we know the Earth is going to radiometric date at 6,000 years because we can pinpoint a decay that happens so fast. Once you account for that, it brings us to. I don't say that at all. The amount of decay I just assume is so small it doesn't make a difference in the debate.
Well, how would you define small?
I want to go back to the control group though. The control group. So it's quite obvious to me when you have terms in the open literature about false isochron, apparent isochron, apparent age, mixing line. Those terms exist because the assumptions that that ratio tells you what you think it does. The fact you have those terms tells you that that assumption must not be altogether true. They have
In what way?
constant ratios too.
Please explain those to each of those terms and why it discredits the isochron dating.
It tells you that you cannot, because an apparent isochron is called that because it appears to be an isochron. That's where the word apparent comes from. It appears to be an isochron, but it's not. If it were a valid isochron, they wouldn't call it an apparent isochron. They'd call it the isochron date.
So is the argument
those
then
ratios? It's specifically because those ratios, that strontium 87, strontium 86 ratio, in specifically in the two daughter isotopes, it's because they are constant and do plot the line that you think an isochron should. But the fact that they exist at all, and they're actually quite common, the fact that they exist at all tells you that that underlying assumption that the ratio tells you the correct history is not right. The assumption is invalid.
Well,
so
it sounds
I'm back to.
Sorry, go on.
Go ahead.
Well, it sounds that you're agreeing with me there that if you have the isochron line, that you are showing that there has been no contamination or nothing, moved in or out. It sounds like you agree with me on that.
I would agree. No contamination and no variable decay.
So if there's no contamination, and we know that those, we know that the only thing in there is rubidium 87 that is decaying, and the only thing that's growing there is strontium 87. What you're essentially asking me to believe is, by sheer coincidence, when we take a sample, a frozen snapshot in time, just a completely sheer coincidence in these thousands and thousands of isochrons, for example, these meteorites, we've just seen dozens and dozens for these same meteorites. You're asking me to believe that by sheer coincidence, we happen to get that just snapshot in time in the individual minerals that were in that rock to make them form a perfect line and fool us all into thinking that that was an isochron. That is the only way what you're saying can possibly discredit isochron dating. And that is asking somebody to believe a whole lot. You know what I mean? That's like somebody winning the lottery every single week for 1 million years. It's just it's asking way too much to believe.
No, that's not actually what I'm asking you to consent to. What I'm back to that whole idea of where's the control group. The fact that you have false isochrons tells you need a different type of control group. And what I'm saying, that control group should have been, from back since radiometric dating was first conceptualized, it should have been a very, very healthy sampling of across the globe of rocks of known age, i.e. specifically like volcanic eruptions that have historical recordings that when the eruption happened, and both from ash and from the lava flows themselves. But they should have been taking very healthy samplings of those and determining what do rocks of known age, what is their isotopic pattern look like in rocks of known age. Therefore, when I go to rocks that I think are much, much older, I can compare that chemistry to what we know to be modern chemistry and deduce. And now I have a control group. Now I have a background reference in which to frame my results in. And my whole point here is that data doesn't exist.
Okay, I think you're misunderstanding slightly what the isochron is. I know I said I wouldn't share screen anymore, but
yes,
and I'll take it down if you've got something to show, because I know I've had it a lot.
you're good, Catz. Yeah, I got it screen shared for you.
Oh, thank you. Okay, so from what I know of you, TRock, you do not deny, like you said before, that decay rates are constant, and you do not deny that stable isotopes don't decay. Like I don't think I've ever heard you say that a stable isotope would decay. So therefore, we know that when that in nature, right? If I've got a rock in my garden over there that's got no rubidium-87 in it, right? That's decaying to strontium-88, it's got none. This ratio here is never going to change, is it? It's going to stay the same because neither of them are going to decay. So what that means is, unless there has been decay, right, these are always going to form a straight line in terms of the y-axis. They're always going to be parallel to the x-axis in relation to the x-axis, right? They're always going to be on that same value on the y-axis for the ratio, because it is constant, they're not decaying. So this is why isochron dating is so good, because we know this is true. We know that whenever that rock was formed, with or without rubidium, this is how that ratio of the two stable isotopes would be. Therefore, when we see it shifted, we know that it's come from this position, unless you're going to change your mind and tell me that strontium-87 and strontium-86 will decay. Okay? But because we know they won't decay, it has to start like that because it's a stable relationship, and therefore only the decay of rubidium-87 can push it in this direction. So that's where we talk about control groups. This is our control, and we see this in nature all the time when we analyze samples of strontium. We see a stable ratio of 87 to 86. So there's our control, and we see it and we measure it all of the time.
So you've given a false dichotomy there. You're basically offering either a stable ratio or you're offering decay.
No. The stable ratio, in the absence of something that's going to decay into strontium-87 or 86. So let's imagine the rubidium isn't there, right? If I could cover up that whole label on the x-axis, I'm going to cover it up, and we're only going to pretend that the sample has strontium-87 and strontium-86. We're only going to pretend that they're in there. Would you agree that if all we had in the sample was these two, that this position of these minerals on the y-axis would never change because all we have in the sample is those two and they're both stable? Would you agree with that?
If all you have is those values, you only have the y coordinate. You don't even have a dot on the graph yet.
Yeah, so but what I mean is they would all have the same y value is what I mean.
Very close, but not identical. That's why you can get a line out of it, because they're not identical, but they are very close.
Well, when we look in nature and we measure, we see this relationship stable, don't we?
Well, that's what I was trying to get at a little while ago,
Yeah.
because you were talking about decay or it's a stable, and I'm saying I called it a false dichotomy because that thing called fractionation. Fractionation doesn't imply that strontium-87 decayed into strontium-86 or anything like that. It's called fractionation because there's an apparent drift of isotopic ratios in rocks.
It's not an apparent
it's well
drift.
documented in open literature.
It's a drift due to the decay of rubidium-87, which we know decays into strontium-87, right? We can see that in real time. We know rubidium-87 decays into strontium-87. So the only thing that's going to shift them, like we both agreed they'd have the same y value coordinate. So the only thing that can stop them having the same y value coordinate is if we get an increase. Well, the only thing that can do this is if we get an increase in strontium-87, and because they're all moving to the left as well, they're moving diagonally, we have to have a decreasing rubidium-87. And if the decreasing rubidium-87 is the same as the increase in strontium-87, then they all move together as a line, and we know there's been no contamination because the increase in one is equal to the decrease in the other. So that is the control.
It's not the control. I don't know how strong your mathematical intuition is, but I pointed this out earlier about having to use a logarithmic scale. There's a drift back and forth. Nobody cares which direction on that slope that it drifts to get the spacing so that you can draw a line out of it. It takes a minimum of two points to make a line segment or a line, to define a line segment or a line, right? These dots are very, very close together because the ratios, and one of the questions I do not know the answer to is how many individual atoms are counted during a radiometric dating test where you're using mass spectrometry. How many individual atoms are counted?
I don't know. It's the ratio.
I don't either, but that's part of the point. That's what I made the example earlier about, 101 to 13 or some number like that of the parent and the daughter. There's some number that they're counting, and it may be very high or it may be very low, but they're not identical, and they're not necessarily supposed to be. But you're getting the spacing because they're slightly different than each other. That in and of itself, if they were perfectly identical, what that would tell you is that you have a perfect isochron, and it would still hypothetically be a valid date.
I'll make this my last thing on the isochron because I know I banged on about it a lot, and I know Donny wants to get to the questions, but I think there's two things here you've said that contradict each other. The first one is when I said these will all be on the identical place on the y-axis, you said they'd all be very close. There will be slight differences, but mathematically they will be very close. Then you said, but there's a logarithmic scale. Now, if you've got a logarithmic scale, then any kind of difference is going to be magnified. But you also said that we need a logarithmic scale to get them on a straight line. So a logarithmic scale would magnify the differences. So how can it make them on closer to a straight line?
No offense, Al, but it doesn't sound like your mathematical prowess is where.
Please explain it to me. Explain to me what you mean then when you say logarithmic scale.
So there's a value called an R-square value. When you do a plot, you can do this in Excel or Google Sheets or whatever. But you can plot a bunch of XY coordinates like this to simulate what an isochron looks like, and then you can tell Excel to give you the to give the best fit line. And when it does that, it generates what's called an R-square value. And the way it's essentially done is some background trig where you're literally triangulating the distance between the points and figuring out what the slope is. And then at the end result, you square it. And you should be getting, in a legitimate isochron plot, you should be getting an R-square value of something like 0.96, whatever. But it's up very close to 1, but not 1 almost ever. If it is 1, that means you have a perfect isochron, but it'll almost always be like 0.96, 0.97. If it's at like 0.85, your R-square value is too low, and it's not a valid line fit. That means that you've got a kind of a squiggly thing going on or something. But that answers your question. You incorrectly represented what I said. I did not say that you have to have the logarithmic scale to get the line. What I said was you have to have the logarithmic scale to visualize it on the graph, but mathematically you can account for it.
Okay, so they're going to be on a straight line anyway, is what you're saying.
They're going to produce, again, you're going to call it a valid isochron if that R-square value is up very close to 1. You're going to call it an apparent isochron if it's up there very close to 1, but the scientist does not think it represents the accurate age, and you're going to call it a non-isochron if the R-square value is too low.
Okay, so again, just so I can try and get this in, try and understand what you're saying here, because I'm not quite sure exactly what you think you're saying, but if we start off here, do we agree that they are all on the same Y value or not?
Again, roughly, they are.
Roughly. Okay. So the difference is minor. Yeah. So let's take some numbers with a minor difference. 2, 3, 4, 5, 6.
Do you understand that it has to be minor? It can't be big because you won't get an R-square value and you won't get a legitimate isochron if it's a big difference.
what I'm asking you, right? Let's say that on the Y value, we have a 2, a 3, and a 4 for these three. Okay. So you are telling me that there's a logarithmic relationship, right? Or there's a logarithmic scale that is going to be applied to these numbers for some reason when the rubidium decreases. I don't know why we only applied to it when the rubidium decreases. I don't understand. But can you now tell me what logarithmic relationship it is, and we'll apply it to these numbers on screen? If you can tell me what the logarithmic relationship is, that would be great.
You're not representing the values correctly. When you put 2, 3, and 4, it shows that you don't understand mathematically what's actually happening.
Well, I was trying to let you do it. I'm trying to show the point that
there's a ratio. So this is fairly easy to conceptualize. If you have a very young rock, you should have, for example, in your example, rubidium, strontium, you should have much more rubidium than strontium in a very young rock, right?
No.
So if you
you shouldn't.
Huh?
No. In a very young, you're talking about like the beginning of like creation rock. Is that what you're talking about?
No, I'm just saying a very young rock. It doesn't matter when in time it happened. What I'm saying
why would you have more rubidium 87 than strontium 86? Why would that have to be?
Because rubidium decays to strontium. Rubidium is
it decays to strontium 87. It doesn't decay to strontium 86.
Sorry. Okay. You get the point, though. When rubidium decays to the next step, rubidium 86, when it decays to that in a very young rock, you have much more rubidium than strontium, right?
Well, not necessarily. It depends on the minerals, but you will have more than when that rock is older, if that's what you mean.
That's what I mean. Whenever it formed, it doesn't matter. The point is, once it's formed and the clock starts ticking on this process, you have to have, by definition, much more rubidium than you do strontium.
No. You have to have some rubidium and you have to have some strontium. It doesn't mean that, because remember, strontium 86 is a stable isotope. So that can exist without any rubidium. I can have a sample of strontium 86 on a desk with no rubidium present.
Okay,
so just because I have a particular rock doesn't mean that because strontium 86 is in there, I have to have a load of, I have to have more rubidium 87. That's not true.
You've bypassed an important step there that either sounds like you don't understand the method or you don't understand what the professional opinion on this is. In a zircon, the whole point of a zircon is that when the crystal forms, it rejects all the strontium that was in that particular unit or in that particular sample. You have to have a starting point at time equals 0. You have to have 0 daughter isotope and 100% parent isotope. Otherwise, this method is completely invalid.
No, you don't. You don't need to know the original starting point. And this is the whole point. You need to know the ratio. And
I didn't say you need to know it. I didn't say you need to know it. I said it has to start that way.
No, it doesn't. It doesn't at all. It absolutely does not at all. We've got rubidium strontium that is being used for this here, right? We've got lead isochrons being used. We've got argon being used. All these are different different workings of isochron dating. So are you telling me on all these different versions you have to have 100% of one thing and 0% of another? I think you're thinking about lead, about I don't know, uranium, potassium argon or something like that. I think you're thinking about something where we're just measuring the ratio of 2 isotopes. One will have been there originally and the other one is radiogenic, right? That's what I think you're thinking about. This is not what's happening on an isochron. We've got 3 different isotopes here. Only one of them is radiogenic, or at least from rubidium 87. Maybe there's a strontium 86 is part of a different decay chain, but it's not part of it's not what rubidium decays into at all.
I apologize, but it really sounds like you've missed the most important point of the isochron plot. The thing that the plot demonstrates is that it proves that you did start out at t equals 0, 100% parent and 0 daughter. No. It's supposed to demonstrate that, because if it does not, you don't know when the rock formed, because you don't know what the initial starting point was. You can't do a half-life calculation.
I've never
cannot
seen
do a half-life
anybody
calculation if you
get
don't know
this
where to
more
stop
wrong.
the clock at.
I've never seen anybody get this more wrong, right? I at the beginning of the video, I really clearly explained that this has got nothing to do. The advantage of isochron dating is that we don't need to know what was present when the rock was formed because we look at the ratios. I don't know why you're saying that there has to be 100% of one and 0% of the other, because that is literally not what isochron dating is. Isochron dating, the strength of it is that all we need is a ratio. I don't know why you're asserting that there has to be 100% of one and 0% of the other. Nowhere in any literature ever, nowhere in any paper, nowhere in any website that details or YouTube video you'll see about isochron dating does it say in any way, shape, or form that you have to have 100% of one and 0% of the other. What you will find is it says the exact opposite. And the exact opposite of that is it doesn't matter what was in to start with. All that matters is the ratio. And why it matters is because the ratio of strontium 87 to strontium 86, because they're both stable isotopes, will put the three on the same point on the y-axis. You can tell me again that we have to have 100% and 0%, but it is just wrong. It is just wrong. And if you're telling me that we have to have 100% and 0%, I mean, I don't know where to go with you. You're just wrong. You just don't understand what this process is. And I don't mean to sound harsh with that, but it is as wrong as you can be.
No, I apologize again, Al, but you're demonstrating your lack of mathematical understanding in how half-life calculations are proceed. The reason for that ratio is to show exactly what I'm saying, and you know that when you understand what the equation looks like. Donnie, I'm trying to share my screen. Do you mind pulling this up?
Oh, sorry. Yeah. Are you still adamant, though, that you need 100% of one and 0% of the other?
I'm going to show you mathematically why that's true. See this equation right here?
Yes.
I'm gonna blow
Yeah,
that
okay, yeah.
Okay, now this particular equation is not radiometric dating, but it is very similar to it. What radiometric dating actually looks like is this equation. See that 0 right there?
Yeah, and then you got exponential to the half-life.
That 0 actually represents is the starting initial condition, and it can either be 100% parent and 0% daughter, or it can be any other percentage of parent and daughter. It doesn't matter.
And that is not isochron dating. That's not what's used in isochron dating. The whole point of isochron dating is that we don't do that because if there's contamination, etc. Isochron dating will allow us to figure out that there's no contamination, but knowing for certain the original starting point is a problem, which is why isochron dating uses a ratio. We simply do not need to know the starting amount. We simply do not need to know it.
You are unequivocally wrong on this.
I'm unequivocally right.
The point of the isochron is to demonstrate that there is no contamination. You've got that part right. But in order to actually assign an age, in order to actually assign the age itself, you have to develop your X and Y, you have to develop your Y-intercept and know where it's supposed to intercept. And this equation is how that age is determined. N sub t is, for example, right now, the amount of time that has passed. N sub 0 is the starting condition. E is the natural number, E 2.87 or whatever it is, raised to the negative KT, where K is the decay constant of that particular isotope, and T is the amount of time that has passed. No. And so you have to have this equation in order to develop that that age. The isochron plot, just having a line intercept the graph doesn't do it. You got to know what the y-intercept value is.
I've just Googled the question. I've just Googled the question in isochron dating. Do we need to know the amount of parent isotope? Shall I share my screen and show what the results say?
Hold on, let me finish my explanation here, because I can predict what I'm going to see in that.
It's going to tell you you're wrong, is what you're going to see.
No, what I'm trying to explain to you is this N sub 0 term. That's the initial condition. If you do not know what the initial condition is, you've got two unknowns in a single equation, and you can't even solve it and get an age. Mathematically, it's impossible to do what you're describing.
Can I just share my screen now? Okay, so here, I've highlighted it for you. In isochron dating, we do not, in bold, need to know the initial amount of the parent isotope. Let me explain how it works. And then it goes on to explain exactly what I've said. We do, let me just read that again. In isochron dating, we do not need to know the initial amount of the parent isotope. We do not need to know the initial amount of the parent isotope. Honestly, I think this is where the issue is. I don't think you know what isochron dating is, which is,
Al,
if you did, you just couldn't be this wrong.
Al, can I ask you a question?
Yeah, go on.
Go on and show me how you mathematically determine what the age is then.
Ah, right. It's the gradient of the line. So because you know, it's or it's derived from the gradient of the line. Let me just get my PowerPoint up. Yeah, that's what I should have said before. Let's just put that to bed, because I know some people in the chat were thinking, oh, Catz, we do not need to know the starting amount of the parent isotope. That's why isochron dating is so good. Okay. As the rubidium decays and the value moves to the left on the x-axis, and as the strontium 87 increases and it moves up on the y-axis, we start to get an increase in the gradient. And the more decay that occurs, the steeper the gradient is. And we know, like we both agreed at the beginning, we agreed about 10 minutes ago that this would be a straight line. So it would have a gradient of 0. In America, you call it slope, not gradient. We call it gradient over here, just in case there's a language thing there. Okay, so the slope of the graph, the gradient of the graph, interchangeable. But the slope of the graph is going to increase the more decay happens. So we can use the slope or the gradient of the graph to determine how old that's been based on the half-life of rubidium 87. That's how it's determined, not by knowing the original.
I'm not even disagreeing with that basic description. I know, I already said that. It has to intercept. And if you go back to your graph that you just showed, the one you made, go back to that graph.
Yeah.
You are practically intercepting, although not exactly. You're almost intercepting the origin. You have to be in the positive area of the y-axis, and then
well, there we go.
You still don't know what the slope even means until you've mathematically solved that equation I showed you.
Right. No, that equation has got nothing to do with it. Listen, I'm going to be honest now. You obviously, and I mean this, I don't, this isn't a personal attack, okay? Because we could have brought up loads of topics I knew nothing about tonight, and I'd have floundered around and I wouldn't have known. But we spent 10 minutes there with you telling me that we needed to know the initial amount of isotope. You told me over and over and over again, you told me I was wrong. You told me I didn't know what I was talking about. You told me that, Al, I don't think you've got a clue. Let me explain this to you. And you told me over and over again that we needed to know the initial amount of parent isotope, despite the fact that I gave the presentation at the beginning. We then looked up, and I've had to Google this in front of you to show that actually, no, you're wrong. We don't need to know it. And given the fact that now we know that we don't need to know it and you were wrong, please don't stick to your guns and tell me that you understand this and that equation you brought up somehow is still relevant when you clearly didn't know the basics of how this is used to date. You clearly didn't know the basics of it. And maybe I should have explained it better at the beginning. But, we've spent 10 minutes of you telling me there that we needed to know the amount of parent isotope. I maybe just accept that, like, all right, you've overstretched a bit.
I don't know how to explain it to you any other way, but you've given me the layman's explanation and you've not shown the math. My personal background, I'm not a mathematical genius or anything, but my personal background is in engineering, and we do a lot of math. And we specifically do examples like this in radiometric decay, and that is how it is done in the textbook to develop the number. You're giving me the layman's explanation, but you cannot show me how you even get an actual age out of that. Okay. How do you even begin to calculate if the slope is 3/1 or whatever? How do you even begin to know how many years that represents? You can't just simply say a steeper slope means more decay or whatever. Actually, a steeper slope means less decay because it's going to point the axes more towards the origin. The flatter the slope gets, the older it is.
I think two things. I think we would all agree the more that rubidium decays, the steeper the gradient gets. we would agree that there is a relationship between the amount of that of rubidium decay to the gradient of that line. So therefore, we'd agree that the steeper the gradient is, the older the rock. Now, have I
will
looked
concede
at?
I think you're right on that point. It can hypothetically get up to a 45-degree line, but either way, you have to have a background calculation to tell you what the Y value is supposed to be.
But it's not the one you were presenting. It's not the one you present, because the one you're presenting, you need to know the initial amount of parent isotope. Now, I teach physics. I used to teach A-level physics in the UK. That equation that you're typing there is on the A-level physics specification. And what that does is it just allows you, when you have a sample of something and you know the original number of radionuclei in that sample and you know the half-life, it just allows you to calculate how many of those you'll have later on. I've had 17, 18-year-old students using that equation, passing physics exams, A-level physics exams, and going off to university. It is not a complicated equation that you were showing us. It is just an A-level physics equation that allows you to calculate how many radioactive nuclei will I have left in a certain amount of time. That's the equation you're putting on the screen. But to use that, you need to know the initial amount. So if you keep going back to that equation, which I have taught 17, 18-year-olds, so I know that equation. If you're going to tell me that we need that, I'm going to tell you you're wrong, because it says that you need to know for that the initial amount. And we've just seen on screen here, we don't need to.
Actually, TRock, before you respond, you guys are very engaging and entertaining. We are into a lot of bonus minutes here. And so I do want to respect your time. You know, great endurance from the both of you. Did you want to have a quick response, TRock, and then we'll jump into closing statements, and then that way we can address some audience questions? Or
sure.
Okay.
Yeah, you're right. We probably need to wrap this up. So Al, you've shown me the layman's explanation. What you have not shown me is how you calculate what the age is supposed to be. So what I would suppose that you should be doing, whether now or sometime in the future, you can get back with me, I don't care, but go dig up the math to show us, with more than one isotopic system, how you calculate back what the y-intercept is supposed to be for a given age. How do you calculate that?
Well, I'll send you a link to the paper on it. In fact, if I'm allowed to post links, I'll post one in the comments of this chat so people can see for themselves when the video is processed.
Sure, fair enough. But let me say it one more way. If you take that parent isotope amount and you take that finished daughter product amount and you plug them into that equation that I showed, you should exactly get the expected age.
Yeah. So can I just ask one thing? And it is a little bit cheeky, but I do think this is important. For that 10-minute period when you were telling me that we absolutely definitely needed to know the amount of parent isotope, and you were telling me I didn't know what isochron dating was, and that I was wrong and you were right, and we absolutely 100% did need to know it, and I was talking nonsense. Do you accept now that actually I was right and you were wrong?
No,
now it's on the screen there.
You're showing me words. You're not showing me the mathematical system.
Oh, well, I'm saying if we Google isochron dating, nowhere, and we Google the question like I've got here, in isochron dating, do we need to know the amount of parent isotope? And when we get the answer, the very, 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 very highly specific answer of, in isochron dating, we do not need to know the initial amount of parent isotope. And nowhere in any of what we can see on this screen here, and please go away and Google this, everybody in the chat, look at this. The initial amount can be determined. We don't even need to know it. It can be determined using isochron dating. Nothing supports what you said.
Nothing supports what you said. Saying.
You said literally, no, you said we need to know the amount. You need to know it. You didn't say, oh, we can use results and work backwards. You said to me, you need to know what that initial amount is. Do you agree now that you don't need to know what the initial amount is because isochron dating just relies on the ratio?
I don't. You are mathematically completely misrepresenting the argument. Anybody can go to the internet and get an opinion and say this is the way it's supposed to work. But that little quote that you highlighted a second ago, it said, indeed, we can figure out the initial. That is what I have been saying all along. If you cannot figure that out, then you cannot get an age out of it.
I think anybody who watches this stream, because we can all rewind the stream. We can all rewind it and hear exactly what you said. For 10 minutes, we can all rewind. And you weren't saying we need to use the isochron to figure out what was at the beginning. You were saying you need to know it. And I was saying to you over and over, no, you don't need to know it. No, you don't need to know it. And you were saying to me, yes, you do need to know it. I don't think you understand this. I don't think your maths is good enough. I don't think you get it. And then when we Googled it, look, it's plain as day.
You're saying the same thing over and over. Send me the mathematical model that gets you the age. Send me your mathematical model that gets you the correct age.
So should we, well, we could do it. We could Google it now and do some research together. And how do we use the gradient of an isochron line to figure out the age of a rock? Should I Google that now? It's on screen.
Ask Donny.
Donny, it's up to you. I don't you, but if you want me
you
to.
guys are the bosses, whatever you want to do. Do you want to maybe, let's do this. Because if I remember correctly, TRock started with the discussion. And so, Catz, let's give you the last word. And then if there is anything, and feel free to Google that if you want. If there is anything left hanging or, any final thoughts, final points you guys wanted to address, you do have 5 minutes each for closing statements. So we can.
Here we go. There's
ahead,
a video. Catz. There we go. It's on screen for you. It's there. Right, so we've got a nice little video, and it's a video of how do we use the slope of an isochron to determine age. So if you Google how do we use the slope of an isochron to determine age, you'll get this is the video. You can play it and you can watch it and you can critique the maths. Right, it's obviously going through that now. So there you go. Right, sorry, Donny.
Well, no, that's good. That was an excellent discussion, very comprehensive, which is what I was hoping for tonight, gentlemen. I've been looking forward to this debate for a while, as I think we need one of those go-to debates on this topic of radiometric dating. Definitely a technical topic, but clearly you guys have put a lot of study into this. So Catz, TRock, I really do appreciate the engaging discussion. We've also had a very engaging lively live chat today. Lots of side debates and some great questions for us to interact with. But before we get to those questions, we will have 5-minute opening statements. So TRock, you kicked us off earlier with your opening statement, and so we'll give you the first 5 minutes for a closing statement. Whenever you're ready, just let me know. The floor is yours.
Okay, I think I'm ready for my closing statement. I appreciate Al. We get a little bit heated, but I appreciate the open discussion there. We didn't get into some of the evidence that I think Al wanted to see and that I wanted to talk about because we spent quite a bit of time on this isochron thing. But some of the stuff I wanted to talk about had to do with carbon-14 dating and creating that control group that the scientific method pretty much demands that you have a control group. Isochron plots are not that control group. The control group has to be much broader than that. There has to be a geological context. And then you also have to compare it to other methods like carbon-14, like historical dating, even things like ice cores and dendrochronology and stuff like that. You have to kind of mesh it all together to establish what your control group is supposed to look like. And isochron plot does not do that. Al, I just went and did my own lookup of that very thing, mathematical modeling of isochron plots, and it is that equation that I was showing. A minor variation on it, but it's exactly that equation. And so you need the control group. Al wanted evidence for a young Earth and how radiometric dating, basically, in my augmented version, how does radiometric dating data support a young Earth? And that is, it has to do with the whole mixing thing. And what do you find in the zircons? One of the big points that I wanted to bring out there was the different colors that kind of correlate to different colors in diamonds. I think officially the argument for isochron dating is that when the crystal forms, the ionic polarity of the daughter element is of the wrong type, so that the crystal formation basically just ejects it, kicks it out, so that the isochron itself starts at 100% parent, 0 daughter. That color variation, though, I compared it to like diamonds. It shows you that there are mineral compositions in there that are very different from one zircon to the next. And one of the finer points that needs to be brought out is that in that assumption that the daughter isotope is rejected from the crystal formation, when you actually look at zircons, they frequently have what they call, quote unquote, and I got this from a secular paper, highly incompatible isotopes of non-radiogenic elements. And so that's what the whole color comparison was about. If they're highly incompatible, that means that their ionic polarity is of the wrong type and they should be kicked out, but they're not. And the difference in colors from one zircon to the next demonstrates that. So I don't want to throw a bunch of new stuff at Al at the very end of the debate, but I did try to bring that out during my presentation, that the color of those zircons matters and it tells part of the story. And in that, when you start comparing those things to the other things I did mention in my presentation, carbon-14 dating, when you compare the two, you get conflicts. How do you resolve the conflict? Al has not shown us how to resolve those conflicts. And the fact that carbon-14 is a default prediction of the YEC paradigm, you have to have carbon-14 because there's only been one full half-life at most for carbon-14 since the age of the Earth. Therefore, you have to find it anywhere where it should have existed in nature, like coal or any ancient specimen that you find, including things like dinosaur soft tissue and diamonds and things like that. It has to be there, and it is. So how does radiometric dating support a young Earth? It's basically correlating carbon-14, a form of radiometric dating, with other forms of radiometric dating and resolving the conflict. So I will yield my time.
Thank you, TRock, for that closing statement. Catz, whenever you're ready, you also have 5 minutes for a closing statement. The floor is yours.
Okay, I'll share my screen. So just back to this. You may, when you look at it, see something similar to what you were trying to show me before. When you look at perhaps this here, looks a little bit similar. And parts of the maths here are to use that equation to determine. Oh crap! It's bugging. What is it doing there? Right, that's my poor internet. I can't stream and do it at the same time. So you'll see small parts of the working out that are similar, but the final equation just isn't the same. Like I said, that is an equation we teach to school children over here, albeit slightly older school children, 17 to 18-year-olds. I have taught that for many, many years to my school children. That is not the equation that is used to determine the age of an isochron. Either that, or I've been teaching these school children wrong for the best part of 20 years, and yet they've still been passing their exams and I've not been sacked. Okay, so it is not. Secondly, I know you talked about getting bit. I don't think it got heated. I think it was fun. I did get frustrated. I will admit, I was frustrated when I was saying that you don't need to know the amount of parent isotope, and you telling me straight for 10 minutes that you did, until we Googled it and it said that you didn't. That was frustrating because I knew that I was right. I knew I was right. And it was frustrating when I knew that I was so 100% right about something that I was being told otherwise, and that I had to resort to Googling it to show everybody I was right. But still, I won't gloat, but I was right. Anyway, sorry for gloated. Couldn't have that. But I just want to bring it back to this because I approached this tonight with a bit of a smile, because the question was one that I don't usually get to debate. Does radiometric dating support young Earth? Usually it's, does radiometric dating prove the age of the Earth or prove the old Earth, etc. So it was quite nice to be able to sit back and say, right, please show me where the evidence is. And I think we established early on that there was no paper. There was never going to be a scientific paper coming forward to say that the Earth was dated at being 6,000 years old. It just wasn't going to happen. So it was going to be a case of picking apart the suitability of radiometric dating to date anything. And of course, TRock did say halfway through the debate, well, I don't think radiometric dating can be used to date anything, which is fine, which means he doesn't believe that it can date the old Earth, but also equally, by definition, he cannot believe that it can be used to show that the Earth is young. So by the very question of that debate, I think the creation side didn't come out on top on the question of that specific debate. But it's not really about that. It was just fun. It was fun and I enjoyed it. And yeah, it is 1 o'clock in the morning, so sorry if I did kind of get a bit animated towards the end, but you know, it's all good. I enjoyed it. So there we go. Thank you.
Okay, thank you very much, Catz. I agree. That was a fun, comprehensive, engaging, and very enjoyable debate. So, Catz and TRock, I appreciate you both giving us a debate to remember on radiometric dating, which is a technical and very focused topic. And yet you both did a good job at keeping us engaged. So good work. Okay, gentlemen, we have some questions. And I think what we'll do with these questions is whoever the question is for, this is typically what we do for format. So let's say the question's for you, Catz. We'll allow you to respond first, of course. TRock, you can provide your thoughts, and then Catz would get the last word. So whoever the question's for gets the last word. And so let's start right at the beginning here. Question comes in from Taylor K. Question for Catz. How can you be sure that an outside force didn't act on these elements that accelerated the decay rate? How do you know it was uniform for billions of years?
Well, I mean, other than very, very extreme examples where you basically turn something into plasma with ridiculous amounts of energy and get to ridiculous temperatures, we cannot change the decay rate of something. We can't do it. So what you're then saying is, how do I not know that some kind of supernatural intervention didn't do it and then hide the scientific evidence of it? Well, if a supernatural being did do it and then hide the scientific evidence of it, then I can't be sure of that. Of course, I can't be sure of that. But the questions of these debates are, what does the science say? And the science doesn't say a supernatural being did this. The science says one thing. So maybe they did and then hid the scientific evidence, which would be a little bit odd, wouldn't it, to do something like that and then make the science mislead all the people that I don't know. So I guess that's your answer. I can't disprove that.
Thank you, Catz. I appreciate it. TRock, the floor is yours. Just make sure to unmute and you're good to go.
So the question is more for an old earther, but for myself, like I said during the debate, I freely grant no appreciable accelerated decay at all. And personally, I think it's a bad argument for a young Earth creationist to appeal to it. And the reason is because it was deduced in no small part by excess helium from Humphrey's study. And his prediction, he made a prediction that it would be there, and it was there. The problem is that it's in basement rock, and granite has only ever been heated once. And there is a legitimate heat problem associated with assuming that it came from accelerated decay. So if you and creationists use that argument, basically it was originally created to endorse the idea of runaway subduction via the secular standard model of what subduction is. But the problem is that you need that accelerated decay out there in the basalts in the ocean. You don't need it in the continental crust. So I don't think it makes for a good argument. It's in the wrong place, and it's associated with creation week, not flood week, which is what the mechanism was proposed for. Instead, what I think has actually happened is the starting condition is just like the Z-pinch experiments. You start out with an appreciable amount of daughter element, and mathematically that equation, it's shown the way that Al showed it, because one of those terms has to zero out at the end. And on the XY plot of an isochron, the zero on the x-axis is t equals 0.
Thank you, TRock. Catz, the question was for you, so you can have the last word if you'd like it.
No, I think it's good. Like I said, I can't disprove that. I can't know it. All I can do is follow what the science says. And if the science has been manipulated by a supernatural being, then I can't do anything about that.
Okay, very good. Thank you, Catz and TRock. Next question comes in, and it's a question for TRock. Andrew Cumming, appreciate the question. Are you aware of the tests that can be done to distinguish mixing lines from true isochrons? as well as other types of false isochrons? Go ahead, TRock.
Well, that's a great question, Andrew. I cannot say that I know definitively exactly what the test is, but what I can say is that when I go download a database, I should see that test with the radiometric data. I should not see things like apparent isochron or time of crystallization or some other weird explanation, because that's just explaining it away without the data.
Thank you, TRock. Catz, go ahead if you had anything you'd like to add.
No. Like I say, I don't really. I mean, this has been a fun debate, and maybe I should kind of brush up on this stuff. But I haven't thought about isochron dating or radiometric dating or anything like that for a long time. Probably since the last debate I had with you, Donny. So, and I've been really busy, But that for next time, I will absolutely look into all of those. It sounds like it's something worth looking at. I guess I wasn't prepared for that.
Hey, good times, right? Time flies by. Those were a couple of good, enjoyable debates, Catz. And those were my more so anonymous days as well. So, wow, that few years ago. Okay, so
if I can, I'll
it's your question. You get the last word. Go ahead.
Let me recap super quick. There are a couple tests that are done to distinguish false isochrons from true isochrons, such as compare it to a fossil in the vicinity in the formation. There's a test. If it's got the wrong fossil, it's a false isochron. If it's got the right fossil, it's a valid isochron. Another test is compare it to its geological context. Did you get a 1.5 billion year isochron age out of a rock that should have only been 500 million years? It's a false isochron because you had to compare it to a geological context. So are there actual chemical tests that can be done? I'm sure they have played with some. Again, they're not typically defined. They're not in like the database that's been kept for years and years and years. They have no sign of that in there. They simply wave it away and call it valid or not valid.
Okay, thank you, TRock. I appreciate it. All right, now we got one for you, Catz. Tolkienomics. Appreciate it. What are the current methodologies for determining the magnitude of self-diffusion coefficients, and do they account for local environmental impact on ion diffusion rate? Technical one here.
No idea. No idea. I don't know. Ask someone else. Stop giving me technical stuff. No idea. Sorry.
There's a PhD level question there.
There is. That's a good one. Yeah.
TRock, do you have any thoughts on that?
Yeah, the methodology is the isochron plot. That isochron plot is literally meant to indicate that there was no, what he calls here, self-diffusion or environmental impact. That isochron plot is literally the test that's meant to do that, but you can still get isochron plots from invalid ratio, invalid dates. The test can look valid. It can look totally valid using the isochron plot method. And the only way they know it's wrong, the only way they truly know it's wrong, is if it does not agree with the fossils or the geology.
Okay, thank you, TRock. Is there anything you wanted, Catz, in terms of a last word?
No, I still don't know. I still don't know the answer. I need a bit longer than that.
No worries. It's been a very technical debate, that's for sure. Okay, here we go. Apologetics 101 question for TRock. How do you reconcile your view with radiometric decay? Can you steelman your position? Go ahead, TRock.
Yeah, so that word decay there is an assumption. Whether you some creationists literally subscribe to the idea of accelerated decay, and I'm saying it's not decay at all. So you are in those two positions, in the old Earth position and in the young Earth position that assumes decay. You're both assuming decay, but the whole point of the Z-pinch conversation was to demonstrate that you can literally start with some other point in this apparent ratio of parent to daughter. You can start at a non-zero point, and you can't tell the difference because it's created that way in nature. So to highlight that, to really steelman my position, my argument, my official argument on apparent radiometric dating is that it starts with at t equals 0 with 0 daughter. There's no accelerator. Sorry, it does not start that way. It starts with an appreciable amount of daughter element. There is no accelerated decay, but I combine that with and per the comments I made about for a young Earth creationist to even claim that, they've got to go to basalts, not granite, in the ocean crust. But I combine that with Humphrey's model of the formation of the Earth out of water. In his model, he's basically assumes that the Earth started out as pretty much pure water. Hydrogen atoms have a magnetic charge. If you flip them into disalignment instantly, you'll induce a magnetic field, but you'll also start gravitationally collapsing and create heavy elements out of it. That part is not part of his model. His has to do with the magnetic field itself specifically. But what I'm doing is combining the two ideas together and saying, okay, we have a magnetic field, but you also get Z pinch out of his model. You get Z pinch because when you induce that magnetic field, you get the Z pinch. And when you get Z pinch and high pressure and high temperature in a gravitational collapse, you're going to do the same thing you get in a Proton 21 lab. You're going to get a non-zero starting point. And so if there's a non-zero starting point, you cannot use the parent-daughter ratios to make any age determination, and it's not decay at all.
Thank you, TRock. Catz, anything you'd like to add to either the response or question?
No, I mean, the question's really about TRock's view, isn't it? But is steelman an American term? What does that mean to steelman your position?
Steelman, if I understand it correctly, is the opposite of a straw man. So you would be laying out your position. Usually steelman would be like, hey, Catz, can you steelman TRock's position on young Earth as an accurately represent it? Is that right, TRock? Yeah.
Give me my strongest argument.
Okay. Yeah. But no, the question was about TRock's personal view. So I can't. Yeah, that's his question. I'll duck out of that one.
Okay, very good. All right, we got one now for you, Catz. Katrina Cook. Question for Catz. How can anything be determined from a ratio if the wholes are unknown?
Because when you've got a relationship between two ratios, like you do with isochron dating, as the amount of rubidium 87 halves, the amount of strontium 87 is going to double. So as one ratio goes down, in proportion, the other ratio is going to change. And as we've seen with the graph there, because we know they're in proportion with each other, when you line up all those minerals on the graph, and that causes a gradient to become a little bit steeper, we find that the change in the gradient, or the slope, as you say in America, the change of the slope on that graph is going to be directly, or not directly proportional. So it's going to be proportional to the decay of rubidium 87. And that's all we need. Because if we know it's proportional to decaying rubidium 87, then we can use that to figure out, because we know the half-life of rubidium 87, then we can use that to determine the age. So you don't need to know the beginnings. I think I explained it better and longer at the beginning of this show, like in my opening statement. I wouldn't have time to go back into it then, but that's the gist of it.
Okay, I appreciate it, Catz. TRock, any thoughts?
Yeah, it's a good question, but here's the deal. In a ratio, the way it works mathematically is if you have some amount of parent-daughter, some amount of parent radiogenic isotope. Let's say you have 10 pounds. The half-life means that after that amount of time has passed, you should have 5 pounds of parent and 5 pounds of daughter. If you divide 5 by 5, you get a ratio of 1, right? And so that ratio of 1 is supposed to calculate your age for you. And that's essentially what the isochron plot does, is it shows that the ratios have been fairly consistent so that they can calculate an actual age from it. Regardless of how you think that calculation is done, that is the point, is to be able to calculate an age from that. And then, but the problem is if I walk up and hand you 5 pounds of parent and somebody else walks up and hands you 5 pounds of daughter, the ratio is meaningless for an age calculation, even though on paper it you would have had to have known where either one of those came from to know that the calculation becomes meaningless at that point. And that's kind of the crux of the debate here, is that they think that the ratio is meaningful, whereas people who actually understand the implications of the method know that it's not. And in the open literature, they acknowledge it's not. But counting isotopes and creating that ratio is about like counting coins and trying to use them to determine how long the bank's been in business. It's completely meaningless if you don't know where the coins came from.
Thank you, TRock. Catz, anything you wanted to add in terms of a final word for the question?
Yeah, just that if you do get that situation like TRock said, where somebody's coming in and giving extra or washing away, parent or daughter isotope, if there's any kind of movement in or out, then that will affect all of the minerals differently, because they all have a different starting amount of the rubidium and the strontium in them. So they wouldn't move together to form a straight line. So we see that, and that's why it's so powerful, because we see that contamination has occurred, and therefore shame, we can't use that because contamination has occurred.
Thank you, Catz. And I think we're down to our last question, which I'm assuming is a question for the both of you, as it's not really specifying anybody. So appreciate the question. One God is now here. Catz, you started with the previous one, so TRock will start with you. Have rubidium radioactive isotopes decayed at the same rate at all times throughout history, or is this assumed? It could kind of be a question for either of you, but TRock, we'll start with you. What are your thoughts?
Okay, so is it assumed now? I've said at the beginning, and I stand by what I originally said. I assume that the decay rate is constant for the sake of the argument, because I don't think it helps their argument at all. But I have to assume that. Is it assumed? It is absolutely assumed. It very well could be that it has some variability to it, and it could be enough. I said it can't determine the difference between 6,000 and 4.5 billion years, but it could hypothetically be the difference between 4.5 and 9 billion, or 4.5 and 3 billion. It could potentially do that kind of change to what the dating is, but it is 100% assumed, and an isochron plot does not clear that assumption.
Thank you, TRock. Catz, go ahead. Floor is yours.
I think we've got to assume it has, because really, and it was mentioned earlier on, unless you bring in the most extreme of conditions, which if they happen naturally would just destroy the Earth, really, really extreme conditions, we can't change the rate of decay. We can't change the rate of the half-life of radioactive isotopes, try as we might. And it would be amazing if we could. Think about how that would work for energy production, etc. It would be brilliant. So it's not as if people aren't trying. So the fact that we've tried and tried and tried and we can't, we've got to assume that, yeah, why would it have been different in the past and just happened to have changed when we have done everything we can and we can't change it?
All right, gentlemen, that was a question for the both of you. You both got an answer, so I appreciate it. And that wraps up tonight's Great Age of the Earth showdown on radiometric dating. I do enjoy these focused debates. So it's just a general Age of the Earth debate. We're able to pick one topic, radiometric dating, and engage it for nearly 3 hours. So I appreciate it. I also appreciate the time you both have given to us, because I know how busy you both are. If we could, some real quick final words, final thoughts. TRock, let's start with you. Again, thank you for doing this. And final words?
Yeah, I'm not going to go back over any of the material at all in the debate for my closing. I appreciate Al taking the time to do this. I know it's late where you're at. Thank you, Donny, for putting it together. Thanks to the audience for getting involved and tuning in. What I would put forth for Al, though, is perhaps in the future we can get a couple of his favorite C14 papers on coal and diamonds, and he could share them with me ahead of time, and so that we both have time to review the paper thoroughly, and then we can come back as a subset to this discussion, because the whole argument of radiometric dating supporting a young Earth has to do with how you tie all radiometric dating together. So I would think it'd be a really fun discussion to get somebody like Al to bring forth a couple scientific papers of his choosing, just that I get to review them well in advance, so that we're both prepared and centered on the exact same article. The other as an extension of this debate, and there's some other things like that we could continue with. But for the immediate context of radiometric dating, I think the C14 discussion is a continuation of this, and I think it would be hugely interesting to go back over some of those papers in the open literature.
Very good, TRock. I appreciate that. Those final words and final thoughts. Catz, it's been great to have you here for tonight again. I know how late it is, so I appreciate it. And also feel free to give a shout out to, if I understand correctly, you have a new debate channel where you're going to be hosting some interesting debates over the next few months.
Yeah, 8 out of 10 Cats. It's called Myself and Doom. It's like we own the channel together, and we're going to host it together. I do want to say that was a really good idea that TRock just come up with. I think the idea, these debates, when you talk about radiometric dating, I thought, well, out of all the techniques, isochron dating is the one I know more. So I'll just keep the debate as much on that as I can tonight. You know what I mean? In other words, TRock might want to speak about other things. So it's easy to get caught out if somebody brings something up and you think, oh God, I wish wish we'd have discussed in advance what exact topics. So his idea of sharing papers with each other and knowing exactly what the battlegrounds are going to be before a debate is a fantastic idea, because then you get more honest representation rather than people feeling like they're caught on the toes or whatnot. So I like that. Now, if you're ever up for doing something similar like this again, I do notice that there's like a simul stream option. Maybe your debate channel and our debate channel could stream the same show together. Somebody from you could host, somebody from myself or Doom could host, and we could make a bit of a big show of it. If you fancy doing this again and under that format, I'll be all up for that.
Absolutely. I think that'd be awesome.
Real quick, sorry. One other thing that I thought I would throw out there in very similar fashion to the whole carbon 14 paper discussion is bring the math, and we can go over the math as well and resolve that part. And I'm not gun shy about doing that sort of thing. If you want to bring that and make a discussion out of that, I think that'd be great.
I can bring the papers for that, but I know that the way that the noise is adjusted for, and yeah, before we were talking, some people saying contamination or background radiation. Noise is really the correct term, isn't it? Wherever it's coming from, that needs cancelling out. That's what the diamonds are for. But that's the way that's adjusted is going to be different depending on the equipment. And I don't think there is like one standard way for that. But I'll certainly get the paper that I had on my PowerPoint, and you can see how they did it.
Yes, we definitely are not shy of those kinds of debates. I think that'd be fun. It would be like bringing in two different viewpoints, two people that share different viewpoints like yourselves, and just really going through these technical papers that you guys would send each other ahead of time. So I like that idea. And also, Catz, I think with your debate channel and this debate channel, I think it would be cool to collaborate and do some simulcast streams. We could probably get and organize some pretty epic debates for the summer. So
maybe even a regular, once every other month or something, like a big event would be nice. I'll have a chat with the co-owner when I get off here, but I'm sure you'll be up for doing something.
Okay, let's do it. TRock, Catz, couple of true professionals, both experienced debaters and both excellent interlocutors. So I really enjoyed this. I know the audience has as well. And okay, share this content around, because these kinds of events are important. Critical thinking is important. So TRock, Catz, again, appreciate the time you've given to us. And we're going to wrap things up here. Everybody, thanks for tuning in. And Standing for Truth is out.